All right. Let's see. We are starting back on System V message queues. I got a little delayed with lunch, but I did get my cardio in, so. But yeah, I hopefully can get through 2 chapters here. That'll take us to through semaphores to shared memory, and then I think I'm gonna take a break at that point to get dinner, and then I'll be back on in the evening after dinner to finish up with shared memory, System V shared memory. So we learned a lot from the introduction. Just some like stuff that we saw, like IPCS lists that current and active IPC objects. IPCS-L gives you the limits. There's also this proc sysv IPC, and that has like, these files that you can read from, and they have similar information to IPCS. There's I think it's IPCRM, and you say MSG, and you give the message ID like 26, and that'll delete the things. So I'm just going to delete the ones that we have active now. And if you do IPCS, you can see everything's deleted. So pretty basic stuff if you have like resources hanging around. The thing with sysv IPC is the resources are stored in the kernel. They persist in the kernel. There's no file system representation other than the proc stuff that I mentioned. Like there's no like, it's not like a name pipe or even like a POSIX message queue that has like a device for it. It's just in the kernel's memory, and if you don't clean it up in your program because it crashes or for whatever reason, those things are just going to hang around until you restart the system. So yeah, that's just some overview of some of the things that we were talking about last chapter. This chapter describes sysv message queues. Message queues allow processes to exchange data in the form of messages. Although message queues are similar to pipes and FIFOs in some respects, they also differ in important ways. So the main way that they differ is that they're message framed already, like the framing is already built into them. They're atomic, whereas FIFOs and pipes have no intrinsic framing of the messages, and they're only atomic up to a certain size, and they're byte streams basically instead of message streams. The handle used to refer to a message, and then the handles are different. Yeah, the handle used to refer to a message queue is the identifier returned by call to get message. These identifiers are not the same as the file descriptors used for most other forms of I/O and Unix systems. Communication via message queues is message-oriented. That is, the reader receives whole messages as written by the writer. It is not possible to read part of a message, leaving the remainder in the queue, or to read multiple messages at a time. This contrasts with pipes, which provide an undifferentiated stream of bytes. With pipes, the reader can read an arbitrary number of bytes and at a time, irrespective of size of data blocks written by the writer. In addition to containing data, each message has an integer type. Messages can be retrieved in the queue in first in, first out order, or retrieved by type. Excuse me. At the end of this chapter, we summarize a number of limitations of System V message queues. These limitations lead us to the conclusion that, where possible, new applications should avoid the use of System V message queues in favor of other IPC mechanisms such as FIFOs, POSIX message queues, and sockets. However, when message queues were initially devised, these alternative mechanisms were unavailable or were not widespread across Unix applications. So I'm going to blast through this because it's obviously like a legacy thing. Consequently, there are various existing applications that employ message queues, and this fact forms one of the primary motivations for describing them. Creating or opening a message queue. The message get system call creates a new message queue or obtains the identifier from an existing queue. The key argument is key generated using one of the methods described in section 45.2, i.e. usually the value IPC private or a key returned by FTOK. The message flag argument is a bit mask that specifies the permissions, table 15.4, page so-and-so, to be placed on a new message queue or checked against an existing queue. In addition, 0 or more of the following flags can be ordered in message flags to control operation of message get. IPC create, if no message queue with the specified keys exists, create a new queue. Exclusive, if create was also specified and the queue with the specified key already exists, fail will error exists. These flags are described in more detail in section 45.1. The message get system call begins by searching the set of all existing message queues for one with the specified key. If a matching queue is found, the identifier of that queue is returned, unless both IPC create and IPC exclusive were specified in message flag, in which case an error is returned. If no message queue is found, then IPC create was specified in message flag. A new queue is created and its identifier is returned. The program listing 46.1 provides a command line interface to the message get system call. The program permits the use of the command line options and arguments to specify all possible abilities for the key and message flag arguments to message get. Details of the command format accepted by this program shown on usage error function. Upon successful queue creation, the program prints a queue identifier, which demonstrates the use of this program. Okay, I'm just skip over the source code here because it's pretty straightforward. Actually, I thought he was going to have an example usage, so maybe just read it really quick. So you could just say, hey, here's the usage, some flags C and X, create an exclusive, and then you give it a file path name. That's for use and generate a key using FTOC. You can give it a key directly, or you can say P for private. So just a lot of different ways of doing things here. And then that's just flag parsing. Pretty much the entire thing is flag parsing. And then we get down here and we just pass everything in. Pretty straightforward. And then print out the message queue ID. Exchanging messages. The message send and message receive system call performs IO on message queues. The first argument to both system calls, message ID, is a message queue identifier. The second argument, message P, is the pointer to the programmer-defined structure used to hold the message being sent or received. The structure has the following general form. So you have a type, which is a message type, and a char star for the text. This definition is really just shorthand for saying that the first part of the message contains the message type, specified as a long integer, while the remainder of the message is a programmer-defined structure of arbitrary length and content. It need not be an array of characters. Thus, the message P argument is typed as void star. Okay, to allow it to be a pointer to any type of structure. Is there length M text field is permitted and is sometimes useful if the information to be conveyed can be encoded solely in the message type, or if the existence of the message is in itself sufficient information for the receiving process. Sending messages. So the one thing I see is missing is a length. So this is basically a void star. So how do you pass in the length? Sending messages. The message send system call writes a message to the message queue. So we get the pointer to message P. Well, let's see an example of using it here. So we got message length here. Okay. Message send. So when we send, we pass in the length. Okay, it makes sense. All right, let's go back here. Message send takes in the message queue ID, the pointer to the message itself, the size of the message, and then some flags. To send a message with message send, you must set the M type field in the message structure to a value greater than 0. We see how this value is used when we discover message receive in the next section, and copy the desired information into the programmer-defined M text field. The message Z argument specifies the number of bytes contained in the M text field. When sending messages with message send, there is no concept of a partial write as with write. This is why the successful message send needs only return 0 rather than the number of bytes sent. The final argument, message flag, is a bit mask of flags controlling the operation of message send. Only one such flag is identified, which is no wait. Perform a non-blocking send. Normally, if message queue is full, message send blocks until enough space has become available to allow the message to be placed on the queue. However, if this flag is specified, the message send returns immediately with the error E again. Message send call is blocked because the queue is full, may be interrupted by a signal handler. Sorry, a message send call that is blocked because the queue is full may be interrupted by a signal handler. In this case, message send always fails with the error E-enter, as noted by section so-and-so. Message send is among those system calls that are never automatically restarted, regardless of the setting of the SA restart flag when the signal handler is established. Writing a message to a message queue requires write permissions on the queue. The program listing 46.2 provides a command line interface to the message system call. The command line format accepted by this program is shown in the usage error function. Note that the program doesn't use the message get system call. We noted that a process doesn't need to use a get call in order to access IPC objects in section 45.1. Instead, we specify the message queue by providing the identifier as a command line argument. We demonstrate the use of this program in section 46.22. Okay. So we just create a structure here. We say its maximum length is going to be 1024 bytes. And then we have a usage error. So basically you call it with -n optional, which is the no wait flag. You give the message queue ID, the type, which is an integer, and then the text itself. Bunch of parsing stuff, mem copying around. This mem copy I don't like. And then you do the send. It'd be nice if you could just slop in the pointer into your structure instead of doing unnecessary copies. Because like right here it's saying, okay, copy from argv here, mtext message length. Why can't you just point to that memory and assign that as the mtext pointer? Yeah. Not sure why you have to do the additional copy there. Okay, receiving message received, system call reads and removes a message from the message queue and copies its contents into the buffer pointed to by message P. Pretty much what you expect. You got message received, message ID, message P, max message size. So basically the size of your buffer that you allocated for the receive, the type, and any flags. And it gives you back the size, which is probably the size of the message so that you can truncate it on your end. The maximum space available for the mtext field of the message P buffer is specified by the argument max message Z. If the body of the message to be removed from the queue exceeds so-and-so bytes and no message is removed from the queue, a message received fails with error E too big. This default behavior can be changed using the message no error flag described shortly. Messages need to be read in order in which they were sent. Messages need not be read in the order in which they were sent. Instead, we can select messages according to the value of the mtype field. This selection is controlled by the message type argument as follows. So you got message type equals 0. The first message of the queue is removed and returned to the calling process. Message type is greater than 1. The first message of the queue is whose message type equals message type P, or message type, is removed and returned to the calling process. By specifying different values for message type, multiple processes can read from a message queue without racing to read the same messages. One useful technique is to have each process select messages matching its process ID. If message type is less than 0, treat the waiting messages as a priority queue. The first message of the lowest M type less than or equal to the absolute value of message type is removed and returned to the calling process. An example helps clarify the behavior of message type when is less than 0. Suppose that we have a message queue containing the sequence of messages shown in figure 46.1, and we performed a series of message receive calls in the following form: message receive ID, message max size, -300 for the type, and 0 for the flags. These message receive calls would retrieve messages in the order 2 type 100, 5 type 100, 3, wait a minute. 2 type 100, 5 type 100, 3 type 100, and 1 type 300. Further called a block since the type of the remaining message 400 exceeds 300. What is it? 46.1. Where's 46.1? Here it is. So we got our type and our message body in the queue position. So if we requested the negative 300, it's saying that we would get 100, 100, 200, 300, or 2531, 2531. Okay. And we never get the last one, which is 4, because it's greater than 300. Further call a block since the type of remaining message 400 exceeds 300. The message flag argument is a bit mask formed by ORing together 0 or more of the following flags. No wait, formed by non-blocking receive. Normally, if no message matching message type is in the queue, message received blocks until such a message becomes available. Specifying no wait flag causes message received to instead return immediately. Okay. But the error no message, the error E again would be more consistent as the error E again would be more consistent as it occurs on a non-blocking message send or a non-blocking read from a FIFO. However, failing with no message is historical behavior and required by SUS v3. Message accept. This flag has an effect only if message type is greater than 0, in which case it forces the completion of the usual operation, that is, the first message on the queue whose M type is not equal to message type is removed from the queue and returned to the caller. This flag is Linux specific and is made available from sysmessage.h only if GNU source is defined, performing a series of calls from the form message received so-and-so on the message queue shown so-and-so would retrieve messages in order of 1, 3, 4, and then block 1, 3, 4. We're saying 100. 1, 3, 4. Okay, makes sense because it's an accept. No error. By default, if the size of the mtext field of the message exceeds the space available, as defined by the size argument, message received fails if the no error flag, a specified message received, instead removes the message from the queue, truncates its mtext field to the max size bytes, and returns it to the caller. The truncated data is lost. Upon successful completion, message received returns the size of the mtext field of the received message. On error, -1 is returned. Example of message queue containing messages of different types. As the message send, if a blocked message receive call is interrupted by a signal handler, then the call fails with the error enter, regardless of the setting of the SA restart flag when the signal handler was established. Reading a message from a message queue requires read permission on the queue. Example program, the program in listing 46.3 provides the command line interface and message received system call. The command line format accepted by the program is shown in the usage error function. Like the program listing 46.2, which demonstrated the use of message send, this program doesn't use the message get system call, but instead expects a message queue identifier as its command line argument. The following shell session just demonstrates the use of the programs in listing 46.1, listing 46.2, and listing 46.3. We began by creating a message queue using the IPC private key and then write these messages with different types to the queue. So we say, hey, I'm going to create a queue, and I do -p. It gives me back a message queue ID. I then take that thing and I write to the type 20, I hear and I forget, and then I write to type 10, I see and I remember, then type 30, I do and I understand. We then use the program listing 46.3 to read the messages with a type less than or equal to 20 from the queue. So we say -t. If we go back to the program text, -t gives us I don't know, that's over here. -t is type. Okay, that makes sense. So we say type 20, so it has to be less than or equal. So we get back I hear and I forget, and I see and I remember. but it came back out of order. We got 10 first because it's a higher priority, because it is a priority. Type is a priority. The last of the above commands is blocked because there is no message in the queue whose type was less than or equal to 20. Oh, it's because we did -20. That's why. Yep. So we continue by typing Control-C to terminate the command, and then execute a command that reads a message of any type from the queue, which pulls out the last element. Great. Next. It's just program text. We don't really care about that. It's pretty much the same thing that we've seen already. Okay, so we got message queue control operations, message queue associated data structure, message queue limits, displaying all message queues on the system. We already did that. Client server programming with message queues, a file server application using message queues. He goes really hog wild on these things. Disadvantages of system V message queues. And finally, summary and some exercises. Okay, message queue control operations. The message CTL system call performs control operations on the message queue identified by message queue ID. Pretty much what you expect. You have a control function, then you pass in the ID, you give it a command, and a pointer to a message queue ID DS buffer. The command argument specifies the operation to be performed on the queue. It can be one of the following. You can do RM, you can do stat, and you can do set. We don't really need to read the details of those. Further details about these operations, including privileges, I don't care about that. This is the program that uses them. So RM is just immediately remove, stat is to do a stat on it, get information, and set is to update fields. Okay, message queue associated data structure. Each message queue has an associated message queue ID DS. DS is for data structure. Okay. It's kind of redundant. Message queue ID DS data structure of the following form. So what do we got here? Got a lot of fields in this associated data. So we got ownership and permissions in the struct. We got some timestamps for send and receive, and change is probably changed to the queue itself, maybe. Number of bytes in the queue, number of messages in the queue, maximum bytes in queue, PID of last send and PID of last receive. Last send PID, last receive PID. Okay. The purpose of the abbreviated spelling MSQ is the name MSQIDDS is to confuse the programmer. This is the only message queue interface employing this spelling. Yeah, MSQIDDS versus MSG in almost everything else. MSQID, MSQIDDS. Okay. The MSG QNUM-T and MSG len-T data types used to type the MSG QNUM and MSG QBytes fields are unsigned integer types specified by SSV3. The fields of the MSQIDDS structure are implicitly updated by the various message queue system calls, and certain fields can be explicitly updated using the message CTL IPC set operation. The details are as follows: message perm. Yeah, I mean, we don't need to go over the structure. It's just a bunch of metadata. All of the above fields are specified SSV3 with the exception of the underscore ones. The program in listing 46.5 demonstrates the use of IPC stat and IPC set operation to modify QByte setting in the message queue. Okay, makes sense. Message queue limits. Most Unix implementations impose various limits on the operation of system V message queues. Here we describe the limits under Linux and note a few differences from other implementations. The following limits are enforced on Linux. The system call affected by the limit and the error at result if the limit is reached are noted in parentheses. System-wide number of message queue identifiers. System-wide limit on specifying maximum number of so these are all encoded under proc let me close the blinds here. Cat proc sys kernel msg mni msg max msg mmb, and I think I've used the mmb, sorry. I think if I do rip grip on MSG Max, I actually use that in my benchmark already. Okay, displaying all message queues on the system. This is just writing a program to do that, but there's already a program that does that. I'm not really terribly interested in reading this. Client-server programming with message queues. At least this is a little bit more interesting of a program. So maybe we read over this, not including the source code, and then we get the disadvantages and then get done with this. I skipped over a lot of this chapter so far. It's just because it's a lot of information that's completely useless because these things are not in common use and they have defects that we'll talk about at the end of the chapter. And you should use POSIX message queues because they're better. They're just generally better. Okay, client-server programming with message queues. In this section, we consider two various possible designs for client-server applications using sysv message queues. So if I was doing a client-server, well, usually client-server implies some type of request-response pattern, in which case you would have the client write its request onto a queue. The client would use its process ID as the type to encode that into the message, and then have the request itself put on the queue. Then the server would then read these messages and then write responses back. So inside the body of the message, I would have some type of request ID that is a monotonically increasing number, integer, and the client would be responsible for sending that in its request. Once the server gets that, it will then respond on the queue with the response and say, here's the PID for the type. The body of the response would have the request ID, so the client could match up requests and responses. And then the client can just do its writes and its reads completely independently and match things up based on the request ID that is in the response. And then the server can just be a multi-threaded server that handles multiple reads off of the inbound message queue and writes to the same queue. Actually, it can't do that. It can't use the same queue for both reads and writes because it might pick up its own so what we can do is use 0 for, we can use the same message queue if we use type 0 for every request that comes in because it has its associated request ID. Then it also needs to encode its process, its PID. And then the server would then write to the PID as the message queue type, and it wouldn't read off of those, if that makes sense. So yeah, I just do vim temp foo. The way I would do is I would have client, it's doing its request right into the queue, and it's going to have its type set to 0, and then inside the request itself, it's going to have its rec ID set to some number, and PID set to, and then some data. So it's going to be doing its writes like this. So it's going to have type 0, same PID, request is now going to be 4, foobar baz quux here. We'll say client A, and then client B is going to be doing its, client B, it's going to be doing, we'll just do a single right here. We're going to say 54321. Its request ID is going to be 111. And here we're going to say ASDF. So we have two clients doing writes, and then we have a server. Just say server. It's going to be doing its request read. These types aren't even part of the message queue, so I'm just going to say like this. Read off of type 0. And then it's going to do its write onto, so say it gets back this message, read type 0 with the PID, and then it's going to do its write type, in this case it'd be 54321. You don't have to include the PID, but you can if you want. And then the request ID comes along with it, and then data QWR. And then this guy's going to do its read off of type 54321. It's going to get back QWR like that, if that makes sense. I need to take a quick bio break. We'll be right back. All right, I'm back. So that would be my overall design of a client server. It could use the same message queue right into type 0 because there's no PID 0 on the system. That's kind of like the kernel's PID. Would be reserved for communicating to the server. The server then read off of that type 0. It would then get the PID of the client so it knows where to write its response to. It would get its requests and data and do whatever it needs to do. And so it can handle all these requests here. I'll go ahead and show the whole thing here. So these will be reads off of that, read off of that, PID 1 2 3 5. Yep. So then this can turn into a write to type 1 2 3 4 5, and then foobar. I could say this thing capitalizes everything. QWER, or say ASDF. So be a write into type 1 2 3 4 5 Baz Quux, and then this guy would get back ASDF. This guy can do a read here, read on 1 2 3 4 5. Get back foobar. Same thing here. This will be a read off of type 1 2 3 4 5, and it will get Baz Quux here. So the server can just be reading off the queue, doing its work, and then writing back to the queue, and it can do that concurrently because it's just reading off of 0, writing onto whatever 0 told it, whatever the message told it. And then the clients, they're similar. They're doing their writes into there and then reading off of their known location. So they could do their reads and writes out of order. So we could have a situation where it's write, read. It could be like that, or it could be read, write. Doesn't really matter. That's the way I would do it. Let's see how they do it. See if there's anything I missed here. In this section, we consider two various possible designs for client-server applications using system view message queues. You could have a client-server application where it's not request-response oriented, where it's more of a streaming setup that still involves clients and servers. In that case, the semantics are different, but this is for request-response. The use of a single message queue for exchanging messages in both directions between client and server. The use of message queues for the server and for each client. The server's queue is used to receive incoming clients' requests, and responses are sent to the clients via individual client queues. So that's similar to the example that we did with named pipes. Since you can use type inside the message queue to segment the message queue, I feel like there's no need for that. Which approach we choose depends on the requirements of our application. We could next consider some of the factors that may influence our choice. Using a single message queue for a server and clients. Using a single message queue may be suitable when the messages exchanged between the server and clients are small. However, note the following points. Since multiple processes may attempt to read messages at the same time, we must use the message type mtype field to allow each process to select only those messages intended for it. One way to accomplish this is to use the client's process ID as a message type for the messages sent from the server to the client. The client can send its process PID as part of its message to the server. Furthermore, messages to the server must also be distinguished by a unique message type. For this purpose, we can use the number 1, which being process ID of the permanently init process can never be the process ID of the client process. I use 0, but I think 1 would be just as fine. An alternative would use the server's process ID as a message type. That's another good one. However, it is difficult for clients to obtain this information. Yeah, that's true. This numbering scheme is shown in figure 46.2. Message queues have a limited capacity. This has the potential to cause a couple of problems. One of these is that multiple simultaneous clients could fill the message queue, resulting in a deadlock situation where no client requests can be submitted to the server, and the server is blocked from writing any responses. The other problem is that poorly behaved or intentionally malicious client can fail to read responses from the server. This can lead to the queue becoming clogged with unread messages, preventing any communication between clients and servers. Using two queues, one for messages from clients to the server and the other for messages from the server to clients, would solve the first of these problems, but not the second. Unless you do non-blocking and timeouts and stuff. Server sends response, M-type. Yep. So for step one, client sends a request to one, including the client PID. Server reads the request from one, and then writes the response to the PID of the client. The client response reads the PID. One of the message queues, using one message queue per client. Using one message queue per client as well as one for server is preferable where large messages need to be exchanged or where there's potential for the problems listed above when using single message queue. Note the following points regarding this approach. Each client must create its own message queue, typically using the IPC private key, and inform the server of the queue's identifier, usually by transmitting the identifier as part of the client's messages to the server. There's a system-wide limit, MSG, M&I, on the number of message queues, and the default value for this limit is quite low in some systems. If we expect to have a large number of simultaneous clients, we may need to raise this limit. The server could allow for the possibility that the client's message queue no longer exists, perhaps because the client prematurely deleted it. We say more about using one message queue per client in the next section. A file server application using message queue. In this section, we describe a client server application that uses one message queue per client. Boom, 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 boom. Sorry, I'm gonna skip over reading the code because I don't think it's necessary. I think the diagrams explain it. In this section, we describe a client server application that uses one message per client. The application is a simple file server. The client sends a request message to the server's message queue, asking for the contents of the named file. The server responds by returning the file contents as a series of messages to the client's private message queue. Figure 46.3 provides an overview of the application. Because the server performs no authentication of the client, any user that can run the client can obtain any of the files accessible to the server. A more sophisticated server would require some type of authentication form of the client before serving the requested file. So we start down here with the client and the server. Server is forking off a child. So step one, client creates a private message queue. So it creates this thing. Step two, client sends a request to the server message queue, which includes the ID of the client queue. So that message goes into the server. Server reads the request. Server creates a child to handle the request. Okay, this is a concurrent. This is a concurrent server, but the concurrency is through multiple processes, which is like the worst way of doing concurrency for servers. Anyways, server child then sends responses to the queue because it got the information from the server message queue over here. It sends its response, and then client reads the response. Listing 46.7 is the header file included by both the server and the client. This header defines the well-known key to be used for the server's message queue. This is just implementation detail. Going over, we could just read the code here. So we've got a request message. It has the client ID, which is the ID of the client message queue. Type is unused, and the file to be returned, which we call it a path name in this situation. And then the response message is just the data for the file. And then the server program, the Grim Reaper, which is a sig child handler. So sig child, this will be when it exits. So when the children exit, we save off the error no, and then we call wait PID, and then at the end we replace the error no. So this might read off multiple children. Something I want to check real fast. Man 3 exit. Here, what happens in a C program when you call exit -1? I saw someone do that recently. Yeah, it goes to exit 255, which I think gets truncated to 127. Or no, it is 255 because it's the low 8 bits. Yeah, that's right. Yeah, I feel like people get confused with that. Okay, so that's just reaping the children, preventing them from becoming zombies. Serve request is probably the function that gets invoked by the child. So it just allocates some memory on the stack, opens up the path name given to it. So the request is provided to it as an argument, opens it for read only, and then sets its data type. It reads into the response data area and then sends a message. And there might be multiple of these message sends if the read is greater than 0, if it's not end of file or an error. And then finally it says I'm going to create a message type end and then just send the end of message. And we're sending it, how do we know where we're sending it? To request client ID is part of the request, obviously. So server just calls message get to create its message queue, and then it sets sig action to set the signal handler for the children so it doesn't have to clean up all the children. Then it goes into an infinite loop where it calls receive. It'll fork off. Receive writes into request here. It'll fork off here, which gets a copy of the memory, copy and write version of the memory. If PID is -1, it errors. If it's 0, it's the client, in which case we serve the request. Once serve request completes, we exit. We do not exec anything here. Parent then continues the loop. Down here, since it's an infinite loop, this will never run unless we hit breaks here. I didn't check for those. In which case we say, hey, remove your message thing. I thought there was a message remove. Let's go. I'm gonna move this into here. We'll say 46. We'll just say mkdir chapter 46 mv foo into chapter 46 slash request response server design .txt. Cut that out. Yeah, looks good to me. I was gonna do man syscalls here and check for MSG. There's a send receive get in CTL. There is no MSG RM. So you have to type in the IPC RM ID here to remove it. Makes sense. I'm not going to read all that. The client has a handler to remove its queue at the end of the program, which it registers at some point. Where does it register that guy? Add exit here. That call right there. Just some argument validation. And then we say, okay, I'm going to get my server ID based on the server key constant, which was up in here in the include file. Then we're going to call message get to get our client message, but in this case we call it a private. Private doesn't prevent other things from accessing it, it just gives you a unique ID. So you get the client ID here, and then you send your message with the client ID and the path name. You just set message type 1, and then you send your message, and then you do your receive, handle your failures. If you fail, you remove it, and then you read all the bytes, do all your message receives and read all your bytes, and then you say, hey, I received this stuff, so and so total bytes, the messages, and then you exit. This is not an infinite looper, it's a one-time caller. So you can run the file server, you can then see that there's a big, is that a file? Cat Etsy services? I don't think I've seen that before. Oh, cool. This is just names for services. So his was 764, mine is much smaller. Must have done some trimming there. We then say, hey, the client, I want your Etsy services, and then it sends it over. And then we can kill the server. Okay, now we're at the good part here. Stuff that is actually interesting. Disadvantages of System V message queues. Unix systems provide a number of mechanisms for transmitting data from one process to another on the same system, either in the form of undelimited byte streams, pipes, FIFOs, and Unix domain stream sockets, or as delimited messages. System V message queue, POSIX message queues, and Unix domain datagram sockets. There's also internet domain datagram sockets. A distinctive feature of System V message queues is the ability to attach a numeric type to each message. This provides for two possibilities that may be useful to applications. Reading processes may select messages by type, or they may employ a priority queue strategy so that higher priority messages, i.e. those with lower message type values, are read first. However, System V message queues have a number of disadvantages. Message queues are referred to by identifiers rather than by file descriptors used by most other Unix I/O mechanisms. This means that a variety of file descriptors based I/O techniques described in Chapter 66, select poll and epoll, can't be applied to message queues. Furthermore, writing programs that simultaneously handle inputs from both message queues and file descriptors based I/O mechanisms require code that is more complex than code that deals with file descriptors alone. We look at one way of combining the two I/O modes in exercise 63.3. The use of keys rather than file names to identify message queues results in additional programming complexity and also requires the use of IPCS and IPCRM instead of LS and RM. The FTOC function usually generates a unique key, but it is not guaranteed to do so. Employing the IPC private key guarantees a unique identifier, but leaves us with the task of making that identifier visible to other processes that require it. Message queues are connectionless, and the kernel doesn't maintain a count of the number of processes referring to the queue as is done with pipes, FIFOs, and sockets. Consequently, it can be difficult to answer the following question: when is it safe for an application to delete a message queue? Premature deletion of the queue results in immediate loss of data, regardless of whether any process might later be interested in reading from the queue. How can an application ensure that an unused queue is deleted? There are limits to the total number of message queues, the size of messages, and the capacity of individual queues. These limits are configurable, but if an application operates outside the range of the default limits, this requires extra work when installing the application. In summary, system view message queues are often best avoided in situations where we require the facility to select messages by type. We should consider alternatives. POSIX message queues are one such alternative. As a further alternative, solutions involving multiple file descriptors based communication channels may provide functionality similar to selecting messages by type, while at the same time allowing for the use of alternative I/O models described in Chapter 63. For example, if we need to transmit normal and priority messages, we could use a pair of FIFOs or Unix domain sockets for the two message types, and then employ select or poll to monitor file descriptors for both channels. Summary. System V message queues allow processes to communicate by exchanging messages consisting of a numeric type plus a body containing arbitrary data. The distinguishing feature of message queues are that the message boundaries are preserved, and that the receiver can select messages by type rather than reading messages in first in, first out order. Various factors lead us to conclude that the other IPC mechanisms are usually preferable to system V message queues. One major difficulty is that message queues are not referred to using file descriptors. This means that we can't employ various alternative I/O models of message queues. In particular, it is complex to simultaneously monitor both message queues and file descriptors to see if I/O is possible. Furthermore, the fact that message queues are connectionless, i.e. not reference counted, makes it difficult for applications to know when a queue may be deleted safely. I will not be doing any exercises on message queues. System V message queues, I should say. All right, that was interesting. Let's go here. I'm going to say it's 965. And we are at 216. So that took us about an hour to get through. 37, 47, 57. Yeah, almost 30, 28 pages. So that was really fast to read. Did no exercises, cruised through the explanation of the programs, read the source code myself. Didn't get into any of the details because, frankly, this stuff isn't in use anymore, so I don't want to waste too much time on it. I just want to get as much high-level information about it as possible, and maybe look at some of the example programs like the client server thing. Okay, so now we're on System V semaphores. So we go through an overview, creating or opening a semaphore set, and then semaphore associated data structure. So very similar style of chapter. Semaphore initialization, semaphore operations. This one actually might be more interesting than the message queue one. Handling multiple block semaphore operations, semaphore undo values. This is the undo list that I've encountered, but I have no idea what it is. Implementing a binary semaphores protocol, semaphore limits, disadvantages of System V semaphores, and then summary, and we're done. So that'll take us to 994. We are at 965. So that's it's about 30, but the same length. Okay. This one might take more than an hour though, because I gotta spend more time on this, because there's some topics in here that I don't fully understand, like the undo stuff. Yeah, I just don't really have any experience with semaphores versus message queues I already have experience with. Okay. System V semaphores. This chapter describes System V semaphores. Unlike the IPC mechanisms described in previous chapters, System V semaphores are not used to transfer data between processes. Instead, they allow processes to synchronize their actions. One common use of a semaphore is to synchronize access to a block of shared memory in order to prevent one process from accessing the shared memory at the same time as another process is updating it. Yeah, it's kind of like if you have a capacity 1 semaphore, that's basically a mutual exclusion lock. So I'm curious why we'd use this over like a few texts. But we haven't covered few texts yet in any depth, so I wouldn't be able to say yet. Okay. A semaphore is a kernel maintained integer whose value is restricted to being greater than or equal to 0. Various operations, system calls, can be performed on a semaphore, including the following: setting a semaphore to an absolute value, adding a number to the current value of a semaphore, subtracting a number from the current value of the semaphore, and waiting for the semaphore value to equal 0. The last two of these operations may cause the calling process to block. When lowering a semaphore value, the kernel blocks any attempt to decrease the value below 0. Similarly, waiting for a semaphore to equal 0 blocks the calling process if a semaphore value is not currently 0. In both cases, the calling process remains blocked until some other process alters the semaphore to a value that allows the operation to proceed, at which point the kernel wakes the block process. Figure 47.1 shows the use of a semaphore to synchronize the actions of two processes that already move the semaphore value between 0 and 1. Okay, we got process A and process B. Process A creates a semaphore, initializes the semaphore to 0. Process B tries to subtract 1 from the semaphore, which blocks it. Process A at a later time adds 1 to semaphore. The subtraction then unblocks, and process B resumes. Both are concurrently running. Then process A tries to subtract 1 from the semaphore. It gets blocked. And then process B continues running at a later time. It adds 1 to the semaphore, which then gets process A to resume. In terms of controlling the actions of a process, a semaphore has no meaning in and of itself. Its meaning is determined only by the associations given to it by the process using the semaphore. Typically, processes agree to the convention that associates a semaphore with a shared resource, such as a region of shared memory. Other uses of semaphores are also possible, such as synchronization between parent and child processes after fork. Yeah, I mean, you use that as like a wait group too. You could set its What you could do is you could using it as a wait group is a little bit tricky. I don't have a direct obvious implementation that is race free, but maybe one will come up in the chapter here. Okay. Overview. The general steps for using a System V semaphore are the following: create or open a semaphore using semget, obviously. Initialize the semaphore in a set using semctl, setval, or setall operation. Only one process should do this. Perform operations on semaphore values using semop. This process uses the semaphore. Typically use these operations to indicate acquisition and release of a shared resource. When all processes have finished using the semaphore set, remove the set from the semctl. It's amazing how much stuff is in the Linux kernel. When all processes have finished using semaphore set, remove the set using the semctl rmid operation. Only one process should do this. So the owner, basically you have to have an owner of the semaphore that manages it. Most operating systems provide some type of a semaphore primitive for use in application programs. However, system V semaphores are rendered unusually complex by the fact that they are allocated in groups called semaphore sets. The number of semaphores in a set is specified when the set is created using the semget system. Oh, that's fun. System call. While it is common to operate on a single semaphore at a time, the semop system call allows us to atomically perform a group of operations on multiple semaphores in the same set. Because System V semaphores are created and initialized in separate steps, race conditions can result if two processes try to perform these steps at the same time. Describing this race condition and how to avoid it requires that we describe semctl before describing semop, which means that there is quite a lot of material to cover before we have all of the details required to fully understand semaphores. In the meantime, we provide listing 47.1 as a simple example of the use of various semaphore system calls. Where's 47.1? Okay, it's just a program. This program operates in two modes. Given a single integer command line argument, the program creates a new semaphore containing a single semaphore. I'm going to stand up here. Been sitting down too much this week. Oh. Okay. I'm going to move this back so I get a little more shade. And I'm going to hit the lights too. Okay. Let's do this one too. There we go. Given a single integer command line argument, the program creates a new semaphore set containing a single semaphore. It initializes the semaphore to the value supplied in the command line argument. The program displays the integer identifier of the new semaphore set. Pretty basic stuff. Given two command line arguments, the program interprets them as, in order, the identifier of an existing semaphore set and a value to be added to the first semaphore, numbered 0, in that set. The program carries out the specified operation on that semaphore. To enable us to monitor the semaphore operation, the program prints messages before and after the operation. Each of these messages begins with the process ID so that we can distinguish the output of multiple instances of the program. The following shell session log demonstrates the use of the program's listing 47.1. We begin by creating a semaphore that is initialized to 0. Sysem demo 0. Semaphore ID of the new semaphore set. Okay, so it's initialized to 0. We can then execute a background command that tries to decrease the semaphore by 2. So we say -2 on our newly created semaphore. This command is blocked because it's already at 0. And then we do an add 3. And that one will about to set up semop at so-and-so. It completed. And then the other one completed. Semaphore increment operation succeeded immediately and caused the semaphore decrement operation in the background command to proceed, since that operation could now be performed without leaving the semaphore's value below 0. Yep. Pretty basic semaphore stuff. I'm not going to go into detail on the code on that one. Yeah, pretty straightforward. Creating, opening a semaphore set. The I'm curious about the set aspect of it, like what the use cases are for a set of semaphores being treated atomically. The semget system call creates a new semaphore set or obtains the identifier of an existing set. So you give it the key and then an integer, which is n sems, and the flag. So n sems would be the number of semaphores in the set. The key argument is a key generated using one of the methods described in section 45.2. If we're using semget to create a new semaphore set, then new sems specifies the number of semaphores in that set. It must be greater than 0. If we're using semget to obtain the identifier of an existing set, then m sems must be less than or equal to the size of the set. It's not possible to change the number of semaphores in an existing set. Less than or equal to. Does that mean that less than or equal to the size of the set? Does that mean that you can create a semaphore set that say has 100 elements, 100 semaphores that are all treated atomically, but then when other processes acquire that semaphore set by the same key, it will then and have like say like n sems set to like 30, it will then only have atomicity to those 30, or will it treat the whole 100? I guess it depends if the atomic operations apply to every element of the set, or if it's just an atomicity guarantee. I'm guessing it's going to be just an atomicity guarantee. The sem flag argument is a bit mask specifying the permissions to be placed on a new semaphore set or checked against an existing set. These permissions are specified in the same manner as for files. In addition, 0 or more of the following flags can be ORed in semflag to control the operation of semget. So we create an exclusive. These flags are described in more detail in so-and-so. On success, semget returns an identifier for the new or existing semaphore set. Subsequent system calls referring to an individual semaphore must be specified. Specify both the semaphore set identifier, the number of the semaphores within that set. Semaphores within the set are numbered starting at 0. Semaphore control operations. SemCTL system call provides a variety of operations on a semaphore set or on an individual semaphore within the set. So you say SemCTL, here's a semaphore set ID. Here's the number of the semaphore, and here's the command with a optional argument, which is a semunarg, union semunarg. Okay, the semID argument is an identifier of the semaphore which set on which the operation is performed. For the operation performed on the single semaphore, the semnum argument identifies a particular semaphore within the set. For other operations, this argument is ignored. We can specify it as 0. command argument specifies the operation to be performed. Certain operations require a fourth argument to semctl, which we refer to by the name arg. In the remainder of this section, this argument is a union defined as shown in listing 47.2, which must explicitly define this union in our programs. We do this in our example programs by including the header file in listing 47.2. Although placing the definition of the sem union in the standard header file would be sensible, Costudying 3 requires a program to explicitly define it instead. Nevertheless, some Unix implementations do provide this definition in sysem.h. Older versions of glibc up to including version 2 also provided this definition. In conformance with Costudying 3, more recent versions of the glibc do not, and the macro sem undefined is defined with a value 1 in sysem.h. To indicate this fact, an application compiled against glibc can test this macro to determine if the program itself defined the sem union. Using calls. So a sem union is a integer or a struct of sem-IDs, DS, data structure, so that's associated data, or an unsigned short, which would be 32 bits, and it's appointed to it, so it's like an array of 32-bit values, and then a sem info pointer. Okay. Costudying 2 and Costudying 3 specify that the final argument semctl is optional. However, a few, mainly older Unix implementations and older versions of glibc prototype semctl as follows. This meant that the fourth argument was required even in cases where it's not actually used. For full portability, we specify dummy final argument to semctl in those calls where it is not required. In the remainder of this section, we consider the various control operations that can be specified for command. Generic control operations. So you got rm stat, remove, stat, or set. That makes sense. Retrieving and initializing semaphore values, get val. As its function result, semctl returns the value of the semnumph semaphore in the semaphore set specified sem-id. The arg argument is not required. Get val, set val, get all, set all. Let's see here. Retrieving and initialize semaphore values. The following operations retrieve, initialize, or initialize the values of an individual semaphore or all of the semaphores in a set. Retrieving a semaphore value requires read permission on the semaphore, while initializing the values required after write permission. Requires alter write permission. If another process is waiting to perform an operation on a semaphore modified by set val or set all operations, and the changes made would permit that operation to proceed, then the kernel wakes up that process. Changes to the value of the semaphore with set val or set all clears the undo entries for that semaphore in all processes. We describe semaphore undo entries in section 47.8. Note that the information returned by get val and get all may already be out of date by the time the calling process comes to use it. Yeah, obviously it's read, what do they call that? there's a name for that. Bug, class of bug. It's like read before use. The name of the class of bug where you read, but the read goes stale, and then you perform an action that makes assumptions based on the stale data. Time of check, time of use. Yeah, that was the name of it. So that would be an example of time of check, time of use. I should have just kept on reading here. It says right here, time of check, time of use, race conditions. Yeah. Retrieving per semaphore information. The following operations return via function result value information about the semaphore of the set referred to by semID. For all of these operations, read permissions is required on the semaphore set, and the argument is not required. So we got get PID, return the process ID of the last process to perform a semop on the semaphore. Is referred to as sem PID value. If no process has yet performed a semop on the semaphore, 0 is returned. Get n count. Return the number of processes currently waiting for the value of the semaphore to increase. This is referred to as a sem n count value. Get z count. Return the number of processes currently waiting for the value of the semaphore to become 0. This is referred to as a sem z count value. As with the get value and get all operations described above, the information returned from get PID, get n count, and get z count operations may already be out of date by the time the calling process comes to use it. Listing 47.3 demonstrates the use of these 3 operations. Let's see how it's over there. So we're about halfway done for the day at this point. Each semaphore set has an associated semID's data structure of the following form. It's got a permissions, some timestamps, and the number of semaphores. Substitute 3 requires all the fields that we show in the semID data structure. Some other Unix implementations include additional non-standard fields on Linux 2.4 and later. The sem and sems field is a typed unsigned long. Substitute 3 specifies the type of this field as unsigned short, and it is so defined in Linux 2.2 and on other Unix implementations. Blah 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 blah. The field of the semID DS structure are implicitly updated by various semaphore system calls, and certain subfields of the semperm field can be explicitly updated using the semctl IPC set operation. Details are as follows: semperm, semotime, semctime, semnsems. In the remainder of this section, we show 2 example programs that make use of the semID DS data structure and some of the semctl operations described in section 47.3. We demonstrate the use of both of these programs in section 47.6. Monitoring a semaphore set. The program listed in 47.3 makes use of various semctl operations to display information about the existing semaphore set whose identifier is provided as its command line argument. The program first displays the time fields from the semID's DS data structure. Then for each semaphore in the set, the program displays the semaphore's current value as well as a sempid and semncount and semzcount values. Okay, I'm not going to read over this source code. Initializing all semaphores in a set, the program I'll read over the source code of like a program that's actually using semaphores for synchronization. So this is just I'll read the next program, which is incorrect and correct initialization. I think that's something that is worth going over. Implementing binary semaphores using semv semaphores. Yeah. Initializing all semaphores in a set. We can glance over these. So I don't want to get too ahead and like not have some of this under my belt. So we basically have this integer that we read from the argv1. We call semctl, give it the semid. So we don't call semget in this program. We receive it as an argument. We give it 0 for its second argument, which if we do man2 on semctl, second argument is a semnum, which is not used as part of the command here is stat. And then argument arg, if we go up here, where's arg? It's argc. Arg is a dummy. Sorry, arg is a sem union. What's odd is it's not a pointer to the union. And I don't think unions are pointer types. Anyways, we're statting it. Usually you pass a pointer to the thing that you're statting. But I guess what's going on here? We got ds that we assign to buffer. Where are we using ds here? I don't even see where we're using ds. We're not. So I guess this is the data structure that gets updated by stat, so that we get a copy of the pointer. Basically, that makes sense. All right. Yeah, that makes sense. Yep. Calc. What's the difference between malloc and calc? Man 3 calc. Forget what calc does. Oh, it's set to 0. The memory set to 0. So it just zeroes out. So we allocate up some space for arg array. And then for each semaphore, we get a bunch of stuff. And semctl returns those values instead of them being written into dummy. Okay. Initializing all semaphores in a set. The program listing 47.4 provides a command line interface for initializing all the semaphores in an existing set. The first command line argument is the identifier for the semaphore set to be initialized. The remaining command line arguments specify the values to which the semaphores are to be initialized. There must be many of these arguments as there are semaphores in the set. Okay. This is set all. So we do our stat up here, and then we call set all. I thought that would set everything to the same value. Oh, okay. That array, j minus 2. Why does j start at 2? Let's see. Oh, because we're skipping over the first element, which is the command. And the first argument, which is used to identify the semaphore. That makes sense. Okay, that's fair enough. All right, let's move on to semaphore initialization. According to SUSV 3, an implementation is not required to initialize the values of the semaphore in a set created by semget. Instead, the program must explicitly initialize the semaphores used by using the semctl system call. On Linux, the semaphore returned by semget are in fact initialized to 0, but we can't portably rely on this. As stated earlier, the fact that semaphore creation and initialization must be performed by separate system calls instead of a single atomic step leads to possible race conditions when initializing a semaphore. In this section, we detail the nature of the race and look at a method of avoiding it based on the idea described in Stevens 1999. So if you are if you're the owner of the semaphore, you just created it, you can initialize it before you create any current actors to operate on it. But I guess what he's saying is that there's a race in between you creating it and you initializing it. That time where it is uninitialized, there could be a client theoretically that is trying to use that semaphore. And that's why you shouldn't even create any other actors. You should be the only actor that knows about it until you've initialized it. Suppose that we have an application consisting of multiple peer processes employing a semaphore to coordinate their actions. Since no single process is guaranteed to be the first to use the semaphore, this is usually meant by the term peer. Each process must prepare to create and initialize the semaphore if it doesn't already exist. Oh, okay, so now you don't have a single owner, you have just peers. Okay, for this purpose, we might consider employing the code shown in listing 47.5. So we do a semget create exclusive, and then if it's not equal to -1, we created it. So then we set val of the semaphore to 0. Else, if it doesn't exist, then we got some other weird error. If it does exist, then we just get the semaphore so that we get the sem ID, and then we start using it, which is down here. Sem op. In this case, the op is to add 1. So once both threads, does the okay, the key is identifying it. one of these guys is going to get it, the other one is not. Or they both, yeah, because they have exclusive. Only one of these guys is going to get it. So what they're saying is before this initialization can happen, this write could happen. So it could get initialized over one of the writes, in which case you wouldn't get all of your operations applied. That makes sense. Okay, the problem with the code in listing 47.5 is that if two processes execute at the same time, then the sequence shown in figure 47.2 would occur. Figure 47.2, where's that at? The next page, yeah. Let's go over to here. So here, we get it and we create it, then we suspend execution. Process B fails to get it because it's already been created, and then does its second get to just read the ID, and then does a semaphore operation to increase it by 1. So now it's at value 1, and then we initialize it back to 0, so now the value dropped to 0, and then he executes his operation, which takes it to 1 again. So instead of being 2, it's set to 1. So that's 1 interleaving. Let's say here, if the first process time slice happens to expire at the point marked so-and-so in the code, this consequence is problematic for 2 reasons. First, process B performs a sem-op on an uninitialized semaphore, i.e. one whose value is arbitrary. Second, the semctl call in process A overwrites the changes made by process B. The solution to this problem relies on a historical and now standardized feature of the initialization of the sem time field in the sem ID's data structure associated with the semaphore set. When a semaphore set is first created, the O time field is initialized to 0 and it is changed only by a subsequent semop call. We can exploit this feature to eliminate the race condition described above. We do this by inserting extra code to force the second process, i.e. the one that does not create the semaphore, to wait until the first process has both initialized the semaphore and executed a semop call that updates the sem time field, but does not modify the semaphore's value. I'll be curious if he's able to do this without spinning. The modified code is shown in listing 47.6. Unfortunately, the solution of the initialization problem described in the main text doesn't work on all Unix implementations. In some versions of the modern BSD derivatives, semop doesn't update the sem time field. Yeah, it seems kind of hackish. So in here, we created it, initializing it to 0, and then perform a no-op semaphore operation, changes the O time. So that's our no-op. Then here, yeah, see, it's going into a spin loop here. It has a sleep 1, so it's not super spinny, but it's still a spin loop, waiting for that condition to occur. Really, a condition variable would be a good thing here to guard the semaphore. But it seems kind of complex to use a condition variable to protect the semaphore instead of the semaphore just being automatically protected. Alright, we can use various variations of the technique shown in listing 47.6 to ensure that multiple semaphores in a set are correctly initialized, or that a semaphore is initialized to a non-zero value. Great. Spectacular. This rather complex solution to race Brace problem is not required in all applications. We don't need it if one process is guaranteed to be able to create and initialize a semaphore before any other process attempts to use it. This would be the case, for example, if a parent creates and initializes a semaphore before creating child process, exactly what I was saying earlier, with which it shares the semaphore. In such cases, it is sufficient for the first process to follow its semaphore get call by a semaphore CTL, set val, or set all operation. Semaphore operations. So we got that and some example code, which is great. And then we got the semaphore undos, implementing a binary semaphore protocol, semaphore limits, and then disadvantages and summary. So we still got ways to go here. So we got till 95, we're at 80, 79, so that'd be 16 pages. So probably like another hour here. We were at 979 at 259. Okay. I feel good about this though, because I blew through the message queue stuff so fast. I mean, I read like 30 pages roughly, 28 pages in like an hour. So, and we just cruised through that material. So I'm anticipating that we get into chapter 48, which is the shared memory chapter, before the end of the day, which would be great. Let me check my stream health here. All right, that looks good. All right, let's continue onward. Semaphore operations. The semop system call performs one or more operations on the semaphores in the semaphore set identified by semID. So we say semop, semID. Here's our operations, which is like some type of array, I think. And then we have a unsigned integer, which is the number of elements in the array. The sops argument is a pointer to an array that contains the operations to be performed, and the nops gives the size of this array, which must contain at least one element. The operations are performed atomically and in array order. The elements of the sops array are structures of the following form. So we have our semaphore number, which is the number that we're performing the operation on, the operation to be performed, and some flags, which is no wait and semundo. The sem number field identifies the semaphore within the set upon which the operation is to be performed. Sem op field specifies the operation to be performed. If sem op is greater than 0, the value of sem op is added to the semaphore value. As a result, other processes waiting to decrease the semaphore value may be awakened and perform their operations. The calling process must have alter write permissions on the semaphore. So the semaphore op is the delta. Let's look at the delta. If semop equals 0, the value of the semaphore is checked to see whether it currently equals 0. If it does, the operation completes immediately. Otherwise, semop blocks until the semaphore value becomes 0. The calling process must have read permissions on the semaphore. If sem op is less than 0, decrease the value of the semaphore by the absolute value of sem op. If the current value of the semaphore is greater than or equal to the absolute value of sem op, this operation completes immediately. Otherwise, sem op blocks until semaphore value has been increased to a level that permits the operation to be performed without resulting in a negative value. The calling process must have alter permissions on the semaphore. Semantically increase the value of a semaphore corresponds to making a resource available so that others could use it, while decreasing the value of a semaphore corresponds to reserving a resource for exclusive use by this process. When decreasing the value of a semaphore, the operation is blocked if the semaphore value is too low. That is, if some other process has already reserved the resource. When a semop call blocks, the process remains blocked until one of the following occurs. Another process modifies the value of the semaphore such that the requested operation can proceed. A signal interrupts the semop call. In this case, error interrupt results. As noted in section 21.5, semop is never automatically restarted after being interrupted by a signal handler. Another process deletes the semaphore referred to by semid. In this case, semop fails with the error EIDRM. We can prevent semop from blocking when performing an operation on a particular semaphore by specifying the IPC no wait flag in the corresponding sem flag field. In this case, if semop would have blocked, it instead fails with the error E again. While it is usual to operate on a single semaphore at a time, it's possible to make a semop call that performs operations on multiple semaphores in a set. The key point to note is that this group of operations is performed atomically. That is, semop either performs all of the operations immediately, if possible, or blocks until it would be possible to perform all of the operations simultaneously. Few systems document the fact that semop performs operations in array order, although all systems known to the author do so, and a few applications depend on this behavior. SUSV4 adds text that explicitly requires this behavior. Listing 47.4 demonstrates the use of semop to perform operations on 3 semaphores in a set. The operations on semaphores 0 and 2 may not be able to proceed immediately. Depending on the current values of the semaphores. If the operations on semaphore 0 can't be performed immediately, then none of the requested operations is performed. The semop blocks. On the other hand, if the operation on semaphore 0 could be performed immediately, but the operation on semaphore 2 could not, then because the IPC no wait flag was specified, none of the requested operations is performed. And semop returns immediately with the error E again. So this is 47.7, which is the next page here. So we have 3 ops. Subtract 1 from semaphore 0, which is here. This is adds 2 to semaphore. And then this is wait for semaphore to equal 0, but it has a no wait on it. So all these operations are all considered atomically. I didn't realize that. That's pretty cool. The sem timed op system call performs the same task as sem op, except that the timed out argument specifies an upper limit on the time for which the call will block. Sem timed op, is that a system call? man syscalls sem. Yeah, sem timed op. Get op timed op ctl msg. There's no timed msg, even though send and receive can block. It might be an argument, and it might be no block. What else? Mem. So memfd. sh, shared memory. SHM. Okay, so let's look at this. We got the semaphore ID, we got the operations we're going to do, and its length, and then a timeout. Makes sense. The timeout argument is a pointer to a time spec structure, which allows the time interval to be expressed as a number of seconds in nanoseconds. You have to specify time interval expires before it's possible to complete the semaphore operation. Then the sem timeout fails with the error again. If timeout is specified as null, sem timed op is exactly the same as sem op. The sem timed op system call is provided as a more efficient method of setting a timeout on a semaphore operation than using set timer plus sem op. The small performance benefit that this confers is significant for certain applications, notably some database systems that need to frequently perform such operations. However, sem timed op is not specified in SUSV3 and is present on only a few other Unix implementations. The sem timed op system call appears as a new feature in Linux 2.6. It was subsequently backported to Linux 2.4, starting with kernel 2.4.2.2. All right. Oops. Okay, here we go. Example program. The program listing 47.4 provides a command line interface to the semop system call. The first argument to this program is the identifier of the semaphore set upon which the operation is to be performed. Each of the remaining command line arguments specifies a group of semaphore operations to be performed in a single semop call. The operations within a single command line argument are delimited by commas. Each operation has one of the following forms: semnum plus value, semnum minus value, and semnum 0. Okay, at the end of each operation, we can optionally include a N, a U, or both. The letter N means include no wait in the flag. The letter U means include undo. We described undo flag in 47.8. Following command line specifies two semop calls on a semaphore set whose identifier is 0. So we say wait for it to be 0, subtract 1, and then 1 subtract 2, but it's not blocking. So that one's just going to fail with E again. First one will succeed, the second one will fail with E again. The first command line argument specifies a semop call that waits until semaphore 0 equals 0. The second argument specifies a semop call that subtracts 1 from semaphore 0 and subtracts 2 from semaphore 1. For the operation on semaphore 0, sem flag is 0. For the operation semaphore 1, sem flag is no wait. Makes sense. I'm not going to read this. I get the gist. And he's going to go over shell examples here for a couple pages. We get into undo then, our binary semaphore, and then limits and disadvantages. Okay, we're making some progress here. I'm starting to run out of steam here though. I think lunch is starting to hit me. I always get tired after lunch. Look how much of this book that I've read. I've read 984 pages. I wonder, will we hit 100 or 1,000? Yeah. If I do shared memory today, I'll hit 1,000. We'll see if I can get through shared memory. I'd like to. That'll keep me on track for, because I started at 921. This would be 1016. So that's about 100, a little shy, 5 shy of 100. But around 120 is going to keep me on track with finishing by Thursday. So really, I mean, I should read to 1041, which would be here. So that'd be memory mappings as well, if I wanted to stay on track with finishing on Thursday. We'll see if I can get up to here. Oh, I am starting to run out of steam though. It's a lot of semaphore stuff. So what have we learned so far about semaphores? Well, there's the semaphore get to create it or to acquire the ID. There's the main syscall, which is a semaphore op, which is an array of operations performed on the semaphores atomically. And then there's a timed op, which just allows that to be performed with the timeout. And then there's some flags that you can pass into the operations. There's the associated data structure. Which semctl can control. And you use semaphores like you use semaphores normally. But they're global to the system in System V, so there can be some races involved that you need to guard against, potentially, if you're trying to initialize something. Initialize the semaphore to 0. That is kind of silly. I mean, Linux initializes it to 0 because they recognize that it's silly to allow the semaphore to be uninitialized. It's like if you create a semaphore, obviously it should be 0 initialized. Or you should have some way of doing that atomically, like create and initialize atomically. Okay, I'm gonna sit down since I'm like running out of steam here. I'm going to have read so much about semaphores by the end of all this POSIX and System V semaphore stuff that I'm going to just be so tired of them. I have semaphores coming out of my ears. Okay, let's read the examples here. So using the program listing 47.8 along with various others shown in this chapter, we can study the operation of System V semaphores as demonstrated in the following shell session. We begin by using a program that creates a semaphore set containing two semaphores, which we initialize to 1 and 0. So we say create them, and we get the identifier here. Then we say using the identifiers, set their values to 1 and 0. We don't show the code of the sysemv create C program in this chapter, but is provided in the source code distribution for this book. This program performs the same functions for semaphores as the program in listing 46.1 performs for message queues. That is, it creates a semaphore set. The only notable difference is that system create C takes an additional argument specifying the size of the semaphore to be created. Makes sense? Next, we start 3 background instances of the program in listing 47.8 to perform sem-op operations on the semaphore set. The program prints messages before and after each semaphore operation. These messages include the time so that we can see when each operation starts and when it completes, and the process ID so that we can track the operation of multiple instances of the program. The first command makes a request to decrease both semaphores by 1. So it'll be able to do that, but because it has to be atomic, it won't perform it immediately. So that one's going to block. In the above output, we see that the program printed a message saying that the sem-op operation is about to be performed, but did not print any further messages because sem-op call blocks. The call blocks because semaphore 1 has a value 0. Next, we execute a command that makes a request to describe decrease semaphore 1 by 1. That's not going to work. That's going to block because it's at 0 currently. This command also blocks. Next, we execute a command that waits for the value of semaphore 0 to equal 0. That's going to block. Again, this command blocks in this case because the value of semaphore 0 is currently 1. Now we use the program listing 47.3 to inspect the semaphore set. So yeah, we got value 1, value 0, and we got a bunch of stuff waiting. We got a 0 count wait and we got a non-zero count wait. I want to know what the 0 count wait use case is used for. Alright, when a semaphore is created, the sem-otime field of the associated sem-ID's data structure is initialized to 0. A calendar time value of 0 corresponds to the epoch, which is why it's that. Because we haven't applied any operations yet outside of initialization. Since the local time zone in Central Europe, examining the output further, we can see that for semaphore 0, the sem-n count value is 1 because operation 1 is waiting to decrease the semaphore value, and sem-z count is 1 because operation 3 is waiting on the semaphore to equal 0. For semaphore 1, the sem-n count value of 2 reflects the fact that operation 1 and operation 2 are waiting to decrease the semaphore value. Next, we try a non-blocking operation on the semaphore set. This operation waits for semaphore 0 to equal 0. Since this operation can't be immediately performed, sem-op fails with the area again. Yeah, because it's non-blocking, it's just going to error out. Now we add 1 to semaphore 1. Okay, this causes 2 of the earlier block operations on block. So, let's see. Operation 1 is waiting for. So I think operation 1 can unblock. Or operation 2, depending on which one gets scheduled. But I'm pretty sure operation 1 can unblock because it's saying it wants that to be, and then this one's bringing it up to 1, so that one's going to, yeah. So one of operation 1 or 2 will unblock. and then operation 3 will unblock because 0 will not be 0. Yeah, 1 and 3, exactly. When we use our monitoring program with respect to state of the semaphore set, we see that semaphore O time field and associated SEM IDs data structure has been updated. And the SEMP PID values, both semaphores have been updated. We also see that SEMCAT, SEM count value for SEM N count value for semaphore 1 is 1, since operation 2 is still blocked, waiting to decrease the value of the semaphore. From the above output, we can see that SEM O time value has been updated. We also see that semaphore 0 was last operated on by process 3661 operation 3, and semaphore 1 was last operated on by process 3659. Finally, we remove the semaphore set. This causes the still blocked operation 2 to fail with the error number EIDRM, which is, it was removed. We don't show the source code for the remove program in this chapter, but it is provided with source code distributed in the book. This program removes the semaphore set identified by the command line argument. Handling of multiple blocked semaphore operations. If multiple processes are blocked trying to decrease the value of a semaphore by the same amount, then it is indeterminate which process will be permitted to perform the operation first when it becomes possible, i.e. which process is able to perform the operation will depend on vagaries of the kernel process scheduling algorithm. On the other hand, if processes are blocked trying to decrease a semaphore value by different amounts, then the requests are served in the order in which they become possible. Suppose that a semaphore currently has a value 0. A process A requests to decrease the semaphore's value by 2, and then process B requests to decrease the value by 1. If a third process then adds 1 to semaphore, process B would be the first to unblock and perform its operation, even though process A was the first to request an operation against the semaphore. In poorly designed applications, such scenarios can lead to starvation, whereby a process remains blocked forever because the state of the semaphore is never such that the requested operation proceeds. Continuing our example, we can envisage scenarios where multiple processes adjust the semaphore in such a way that its value is never more than 1, with the result that process A remains blocked forever. Starvation can also occur if a process is blocked trying to perform operations on multiple semaphores. Consider the following scenario performed on a pair of semaphores, both of which initially have the value 0. Process A makes a request to subtract 1 from semaphore 0 and 1, which blocks. Process B makes a request to subtract 1 from semaphore 0, blocks. Process C adds 1 to semaphore 0. And so B will proceed and A will be starved out, essentially. At this point, process B unblocks and completes its request, even though it placed its request later than process A. Again, it is possible to devise scenarios in which process A is starved while other processes adjust and block on the values of the individual semaphores. Semaphore undo values. This is something that I'm completely unaware of. So we got reading on that, and then implementing the binary semaphores protocol, the limits, disadvantages, and summary. Okay, we're almost done with this. Suppose that having adjusted the value of a semaphore, e.g. decreasing the semaphore value so that it is now 0, a process then terminates, either deliberately or accidentally. By default, the semaphore's value is left unchanged. Having adjusted the value of a semaphore, Okay, I decrease it to 0. Oh, it's basically like a deadlock. Like I acquired the lock, but I never return it. By default, the semaphore's value is left unchanged. This may constitute a problem for other processes using the semaphore, since they may be blocked waiting on that semaphore, that is, waiting for the now terminated process to undo the change it made. To avoid such problems, we can employ the sem undo flag. When changing the value of a semaphore via semop, when this flag is specified, the kernel records the effect of the semaphore operation and then undoes the operation if the process terminates. The undo happens regardless of whether the process terminates normally or abnormally. That's a neat feature. The kernel doesn't need to record a record of all operations performed using sem undo. It suffices to record the sum of all the semaphore adjustments performed using sem undo in a per semaphore per process integer total called the sem edge semaphore adjustment value. When the process terminates, all that is necessary to subtract this total from the semaphore's current value. Since Linux 2.6 processes threads created during using clone share sem edge values, if the clone sysvsem flag is employed, such sharing is required for a conforming implementation of POSIX threads. The NPTL threading implementation employs clone sysvsem for the implementation of pthread create. When a semaphore value is set using the semctl set val or set all operation, the corresponding sem adj adj values are cleared, i.e. set to 0, in all processes using the semaphore. This makes sense since absolutely setting the value of a semaphore destroys the value associated with the historical record maintained by the sem edge total. A child created via fork doesn't inherit its parents' sem edge values. It doesn't make sense for a child to undo its parents' semaphore operations. On the other hand, sem edge values are preserved across an exec. This permits us to adjust the semaphore value using sem undo, and then exec a program that performs no operations on the semaphore but does automatically adjust the semaphore on process termination. That's neat. This can be used as a technique to allow other processes to discover when this process terminates. That's pretty cool. I'm not gonna lie, that's a neat feature. I like the semaphore sets, I just don't have a use case for them off the top of my head. And the atomicity guarantees of all the operations, that's pretty cool. And then the semaphore undo stuff is pretty cool. Okay. Example of the effect of sem undo. The following shell session log shows the effect of performing operations on two semaphores, one operation with the sem undo flag and one without. We begin by creating a set containing two semaphores that we initialize to 0. So we create two semaphores, then we initialize them to 0. Next, we create a command that adds 1 to both semaphores and then terminates. The operation on semaphore 0 specifies the sem undo flag. So I'm going to say, hey, 0, I'm going to add 1 to that. And then 1, I'm going to add 1 to that too, but only 0 is going to be undone. Now, when we use the program listing 47.3 to check the state of the semaphores, 0 is now 0, and 1 is permanently locked to 1. So 1 is messed up. It's kind of deadlocked. Looking at the semaphore values in the last two lines of the above output, we can see that the operation semaphore 0 was undone, but the operation semaphore 1 was not undone. It's kind of weird they have to explicitly ask for it. I don't know. Maybe it's not too weird. We conclude by noting that the sem undo flag is less useful than it first appears. for two reasons. One is that because modifying a semaphore typically corresponds to acquiring or releasing some shared resource. The use of sum-undo on its own may be insufficient to allow a multiprocess application to recover in the event of a process unexpectedly terminates, unless process termination also automatically returns the shared resource state to a consistent state, unlikely in many scenarios. Undoing a semaphore operation is probably insufficient to allow the application to recover. The second factor limiting the utility of sem-undo is that in some cases it is not possible to perform semaphore adjustments when a process terminates. Consider the following scenario applied to a semaphore whose initial value is 0. Process A increases the value of the semaphore by 2, specifying the sem-undo flag for the operation. Process B decreases the value of the semaphore by 1 so that it has the value 1. Process A terminates. It can't go negative. At this point, it's impossible to completely undo the effect of process A's operations in step 1, since the value of the semaphore is too low. There are three possible ways to resolve this situation. Force the process to block until the semaphore adjustment is possible, decrease the semaphore value as far as possible, and exit. Exit without performing any semaphore adjustment. I would say just like let the kernel continue with its like a background task where it's just gonna like monitor the semaphore until it grows to a value and then prioritize the subtraction. The first solution is feasible since it might force the terminating process to block forever. Is infeasible. Yeah. Linux adopts a second solution, decrease the semaphore value as far as possible. Some other Unix implementations adopt the third solution. Susv 3 is silent on what an implementation should do in this situation. Well, it's nice. An undo operation that attempts to raise a semaphore's value above its permitted maximum value of 32,767, the set VMX limit described in section 4710, also causes anomalous behavior. In this case, the kernel always performs the adjustment, thus illegitimately raising the semaphore's value above sem VMX. Implementing a binary semaphores protocol. The API for systemd semaphores is complex, both because semaphores can be adjusted by arbitrary amounts, and because semaphores are allocated and operated upon in sets. Both of these features provide more functionality than is typically needed within applications. And so it's useful to implement some similar protocols, APIs, on top of systemd semaphores. One commonly used protocol is binary semaphores. A binary semaphore has two values, available, free, reserved, and use. Two operations are defined for binary semaphores. Reserve, attempt to reserve the semaphore for exclusive use. If the semaphore is already reserved by another process, then block until the semaphore is released. Release, free the currently reserved semaphore so that it can be reserved by another process. In academic computer science, these two operations often go by the names P and V. The first letters of the Dutch terms for these operations. This nomenclature was coined by the late Dutch computer scientist Edsker Dijkstra, who produced much of the early theoretical work on semaphores. The terms down, decrement the semaphore, and up, increment the semaphore, are also used. POSIX terms the two operations wait and post. A third operation is also sometimes defined, reserve conditionally, making a non-blocking attempt to reserve the semaphore for exclusive use. If the semaphore is already reserved, then immediately return a status indicating that the semaphore is unavailable. In implementing binary semaphores, we must choose how to represent the available and reserved states and how to implement the above operations. At moments, reflection leads us to realize that the best way to represent the states is to use the value 1 for free, and the value 0 for reserved, with the reserve and release operations decrementing and incrementing the semaphore value by 1. Listing 47.9 and listing 47.10 provide an implementation of binary semaphores using system V semaphores, as well as providing the prototypes of the functions in the implementation. The header file listing 47.9 declares 2 global Boolean variables exposed by the implementation. The BS use sem undo variable controls whether the implementation uses the sem undo flag and sem op calls, and the BS retry on enter variable controls whether the implementation restarts sem op calls that are interrupted by signals. Okay. This is our binary semaphore thing. Sorry, I'm on the wrong page here. Alright, so we got a binary semaphore H. If not defined, check. So we have Boolean BS use semaphore undo and BS retry on enter. We do init sem available, init sem in use, reserve sem and release sem. These are the implementations. Listing 4710 shows the implementation of the binary semaphore functions. Each function in this implementation takes 2 arguments, which identify a semaphore set and the number of a semaphore within the that set. These functions don't deal with the creation and deletion of semaphore sets, nor do they handle the race conditions described in section 47.5. We employ these functions in the example programs shown in section 48.4. Oh, interesting. So we're going to use this to protect our shared memory. They mentioned that earlier. All right. Alrighty, we're almost done here. So, we're going to say semaphore undo is false by default, and retry on enter is true. Okay. Init semaphore available, semaphore and semaphore ID. Well, that is going to be a stack allocation of the union sem un, and we're going to assign in this value, and we're just going to copy that right into this semctl, and we're going to say, hey, set value to 1. That inits it to 1, to being available. In use is the exact opposite, where we just set it to 0. And then reserve the semaphore. In order to do that, we need to do a blocking call, and the blocking call needs to check its error code to see if it was interrupted by the kernel. So we allocate our semaphore buff for operation, and then we set our semaphore number and our ID as it goes over here. Operation is -1, which will be to reserve it. And then we put our undo flag in there if we have that pound defined set. We then go into while, where we perform semaphore operation. Semaphore ID, semaphore op. I don't know what this one is. What is one again? I forget. Why do I forget what that? Oh, it's the length. The length of how many operations. And then release semaphore is the exact inverse, where it's just doing an add instead of a subtraction, increment instead of a decrement. And why is it that we don't need a retry here? Because releasing is always gonna succeed. I would like to know if that's true or not. Like, I think this semop could still error out and need to be resumed. Pretty sure. Okay. Semaphore limits. Most Unix implementations impose various limits on the operation of System V semaphores. The following is a list of the Linux semaphore limits, the system call affected by the limit, and the error that results if the limit is reached are noted in the parentheses. So a bunch of limits. I don't really care. The limits above appear in most Unix implementations. Some Unix just a bunch of limits. Don't really care. We'll read the text. At system startup, semaphore limits are set to default values. These defaults may vary across kernel versions. Some distribution kernels set different defaults from those provided by vanilla kernels. Some of these limits can be modified by changing the values stored in Linux-specific proxys kernel sem file. This file contains 4 space-delimited numbers defining in order the limits and blah blah blah. Okay. A related Linux-specific operation, sem info retrieves sem infrastructure that contains information about actual resources used for semaphore objects. Example of the use of sem info is provided in the file svsem infoc in the source code distribution of the book. Details about info and sem info and the sem info structure can be found in the semctl manual page. All right, now we're to disadvantages. All right, this is the important bit. System V semaphores have many of the same disadvantages as message queues, including the following. Semaphores are referred to by identifiers rather than file descriptors used by most other Unix IO and FIC mechanisms. This makes it difficult to perform operations such as simultaneously waiting on both a semaphore and on input from a file descriptor. It is possible to resolve this difficulty by creating a child process or thread that operates on the semaphore and writes messages to a pipe monitored along with other file descriptors using one of the methods described in chapter 63. The use of keys rather than file names to identify semaphores results in additional programming complexity. The use of separate system calls for creating initializing semaphores means that in some cases we must do extra programming to avoid race conditions when initializing a semaphore, which is silly. The kernel doesn't maintain a count of the number of processes referring to a semaphore set. This complicates the decision about when it's appropriate to delete a semaphore set and makes it difficult to ensure that an unused set is deleted. The programming interface provided by System V semaphores is overly complex. In the common case, a program operates on a single semaphore. The ability to simultaneously operate on multiple semaphores in a set is unnecessary. Hold on. Let me read that. My mind was wandering. The programming interface provided by System V semaphores is overly complex. In the common case, a program operates on a single semaphore. The ability to simultaneously operate on multiple semaphores in a set is unnecessary. There are various limits on the operation of semaphores. These limits are configurable, but if an application operates outside the range of the default limits, this nevertheless requires extra work when installing the application. However, unlike the situation with message queues, there are fewer alternatives to System V semaphores, and consequently, there are more situations in which you may choose to employ them. One alternative to use semaphores is record blocking, which we describe in chapter 55. It's file record blocking. Also from kernel 2.6 onward, Linux supports the use of POSIX semaphores for process synchronization. We describe POSIX semaphores in chapter 53. Summary. System V semaphores allow a process to synchronize their actions. This is useful when a process must gain exclusive access to some shared resource, such as a region of shared memory. As we'll see in the next chapter. Semaphores are created and operated upon in sets containing one or more semaphores. Each semaphore within a set is an integer whose value is always greater than or equal to 0. The semop system call allows the caller to add an integer to a semaphore, subtract an integer from a semaphore, or wait for a semaphore to equal 0. The last two of these operations may cause the caller to block. A semaphore implementation is not required to initialize the members of a new semaphore set. So an application must initialize the set after creating it. When any of the number appears, preprocessors may try to create and initialize the semaphore. Special care must be taken to avoid the race conditions that result from the fact that these two steps are performed via separate system calls. Where multiple processes are trying to decrease a semaphore by the same amount, it is indeterminate which process will actually be permitted to perform the operation first. However, where different processes are trying to decrease a semaphore by different amounts, the operation completed in the order in which they became possible, and which may need to take care to avoid scenarios where a process is starved because the semaphore value never reached the level that would allow the process operation to proceed. The sem undo flag allows a process semaphore operation to be automatically undone on process termination. This can be useful to avoid scenarios where a process accidentally terminates, leaving a semaphore in a state that causes other processes to block indefinitely, waiting for a semaphore's value to be changed by the terminating process. System V semaphores are allocated and operated upon in sets and can be increased and decreased by arbitrary amounts. This provides more functionality than is needed by most applications. A common requirement is for individual binary semaphores, which take on only the values 0 and 1. We showed how to implement binary semaphores on top of System V semaphores. They're just a length 1 semaphore. It's mutex. All right, bunch of exercises I'm not going to do. All right, System V shared memory. Let's go ahead and record our time here. So we are on page 997. And it is 3:52. So that's about an hour to get from 80. So that's about 18 pages. Yeah, 18 pages an hour. That's pretty good. All right. we need to definitely read shared memory, which will take us to, that's memory mappings. Let's see. Shared memory will take us to page 16. So we say 15. Yeah, about 17 pages. Yo. Just got up. Man, you getting up early. This is 3 a.m., 4 a.m. your time, roughly. That's early for you. Yeah, I just got to chapter 48, System V Shared Memory, which is about 17 pages. And then once I'm done with that, I'm basically hitting my target of 100 pages for the day. But I'm thinking about reading memory mappings as well, depending on how much time I have remaining in the day. So this is going to take me at least till 5 p.m. So I might eat dinner and then come on for like a later session just to read memory mappings. Yeah, grinding, changing everything. What went wrong? Nothing went wrong here. Yeah, we got through the introduction of System V IPC, System V message queues, and semaphores. Oh, no, about yourself. Okay, cool. Yeah. So yeah, shared memory. If you're not familiar with like semaphores are like kind of like a mutex that can be acquired by multiple entities, and at least that's the way I look at it. And they describe like this implementing a binary semaphore, which is basically a mutex, and they're going to be using that binary semaphore to guard access to shared memory. So semaphores are like a superset of the functionality of a mutex. And message queues, we've talked about different messaging stuff. They're pretty basic. Shared memory I'm interested in, but again, this is System V stuff. And like System V stuff, my understanding is that it's legacy. It's not really used very frequently. What is a mutex? Mutex is a mutual exclusion lock. So the idea is like in a concurrent system, you have multiple different threads of execution that require access to shared resources. Those resources have to be guarded. Their access to those resources have to be guarded by a mutex. So when you go to access, say like memory that's shared, like in this chapter, if you had two concurrent actors writing, or even just one concurrent actor writing and another one reading, you can have a lot of problems arise from that. Those are referred to as data races. And basically like a canonical example would be a torn read or a torn write, where you're writing, say, 64 bits of data and 32 bits lands into main memory, like the high order 32 bits, but the other low order 32 bits are not, in memory yet, and the other actor reads those 32 bits. So yeah, you can have situations like torn reads, torn writes. You can have the read, modify, write problem, where one process will read the value and then modify it, but the write won't happen immediately. And then the other process will do the same thing, read and modify. And then the first process does its write, and then the second process does its write, and that write overwrites the write of the first process. A good example is like if you ever use like an online spreadsheet application like Google Sheets, where you're like collaborating with someone else on like a Google Sheet. if you go into a cell, here, I'll show you here. I think I have docs.proton.me, I think. Is that a thing I have? No. Docs.google.com. No, I don't have anything logged in here. But if you ever use like Google Sheets, you can see like when one person goes in and modifies a cell, Google Sheets will gray that cell out, and that's like the lock is being applied to the cell, basically. So mutexes are locks. Usually they have like two methods, a lock method and an unlock method. The lock method will block until the mutex is available, and then the unlock releases, it doesn't block, it releases the lock back to whoever needs it. So if you understand like basic mutual exclusion locks, then semaphores are kind of like a mutual exclusion lock, but you can have multiple concurrent actors acquiring the lock. So say the semaphore has a length of 10, you could have 10 different concurrent actors acquiring the semaphore. So a semaphore of length 10 would not be a good tool for protecting memory access, like a mutual exclusion lock. But where I've used semaphores in the past is like in the programming language Go, you can spin up like tens to hundreds of thousands of Go routines. They're very lightweight. And say you're talking to a server, and that server can only handle like 10 connections or 10 requests at the same time concurrently. Then you can introduce a semaphore that says, out of all this 100,000 actors, they're trying to get access to these 10 concurrent spots. We'll just make them acquire a length 10 semaphore. And that way they're all kind of like waiting for the semaphore to be acquired. And once they get it, they're able to communicate with the server. But the server is never overloaded, if that makes sense. That's like a common use case, is to limit the concurrency of the system to a certain bound. In Go, you can use channels to implement semaphores. That's what I've used them before. So channels in Go are used for a lot of different things. You can use them for signaling. You can use them for semaphores. You can use them for a lot of stuff. As a thread safe queue to transport data. There's a lot of things. Now I get it. They will be in queue. That doesn't cause bottlenecks on the system performance. Yeah. When you're waiting to acquire the semaphore, or when you're waiting to acquire the mutex, the Linux kernel will deschedule the thread of execution so that it's not consuming any resources. So overall, like, it's not wasteful, but it will limit the concurrency of the system. So it will affect performance. But if the alternative is that you overload the downstream system, then it doesn't matter what your performance is, because the downstream system is overloaded, it's going to break. Yeah. So in that situation, you can only get so much performance out of the system. But yeah, there's a bunch of ways to implement mutexes. There's like spin locks. Spin locks are fun to implement. They're very easy. So if you've never done that and you're curious about it, that's like the basic lock, is a spin lock. And the problem with spin locks is that they are active on the CPU, which means that they're consuming resources. They're consuming the Linux kernel has them running on a CPU core. So spin locks are very bad. They're used in only very few situations, but once you implement a spin lock, which is really easy to implement, then you can understand the rationale for why a mutex is really valuable. Because if you are using a spin lock, you'll see your CPU just like go all the way up, especially if it's super aggressive. So I don't know how much this interests you, but if you're interested in learning more, I would definitely start with implementing a spin lock. You can just go online and search for like Golang spin lock. It's a good exercise. I did it before, like a long time ago, but obviously implementing it yourself using like compare and swap on a bit of memory. Yeah. And then this go sketch here. You definitely want to do that because it gives the runtime the ability to reschedule the go routine, or else the spin lock will actually take up that core and never release it. So there will be load time and execution when a new process is added to the queue. I'm not sure exactly what you mean by that. Let me try it. Yeah, I guess I'm gonna get a Scala draw. Let me just like oh, I was doing some other drawing here. Well, I'll just hide that up here. I don't know what that was for. So a mutual exclusion lock would be like, say we have like a buffer of memory. It's just a bit of memory. It's global to the process. Here, I think if I double click on this, yeah, buffer. And then say we have a thread A and we have thread B over here. And we both want to, or let's just say like thread A wants to read from the buffer. If thread A and thread B both want to do reads, then there's no problem. If everyone's doing reads, there's no issue. You don't have to synchronize access. You just perform your reads. That's safe. But if one of these threads is trying to do a write, then you have all of these implications of like torn, reads, writes. You have stuff like read, modify, write bugs. You have overwriting. You have a lot of issues. So to prevent those issues from occurring, you introduce a little thing on the side here called a mutex. Actually, I'll put it down at the bottom here just to make it a little bit easier to diagram. It says mutex. The analogy I like using is like if you're eating dinner, it's like you're eating dinner with someone else and there's only one salt shaker on the table. Only one of you can be using the salt shaker at any given time. And so what a mutex guarantees is that you're not fighting for the salt shaker. That's like a super basic analogy. So what happens with this example is that, and I'll label these. So step 1, thread A will acquire. So I'll say 1 acquire. QU. See if I can spell right. It'll acquire the mutex. And then step 2, it'll perform its write. And then step 3, it will release. Release. Step 4 will be thread A will then do its acquire. So that'll be step 4 here. And then step 5 will be the read. And then step 6 will be the release. So we do thread A acquires, and only one will acquire. So if thread B does its acquire, if thread A does its acquire first, if thread B does its acquire first, thread A's acquire will be blocked. So this acquire cannot happen until thread B releases. So that's why it's 4, which is after 3. So thread B gets its acquire in, thread B does its write, it then does a release. Thread A gets its acquire in, it does its read, and then releases. If that makes sense. And then the idea of a semaphore, this is good. I need to get better at explaining things. So this is a mutex. I'm going to copy this over here, and we'll do one for a semaphore too. So semaphore, delete this. So instead of a buffer, the shared resource in this thing will be like a slow server. And we'll do the same acquire release thing, but we'll have maybe 4 threads here. We'll do thread C and thread D. So all 4 of these threads are trying to do, let me delete all this stuff here. So say it's like an HTTP server, and it can only handle 2 requests per second, or two concurrent requests. Any more than that, the server just panics. It just like crashes. We'll say, or else crash, and then nothing happens. Also save these images in notes with PNGs. Yeah, I need to, I'll do that after the stream is over. I'll just go in and save these because I had some other stuff here that I forgot about. Okay, so we got thread A, thread B, thread C, and thread D. And we got a server that this server can only handle 2 concurrent requests. So if all 4 of our threads are running and trying to make these post requests to the server, then basically the server is going to die, which isn't what we want. We want the server to be alive because it's doing work for us. So I gotta get all these things attached or else it annoys me. All right, there we go. So this thing does not work. This is bad. Server crashes. So what we can do instead is we can introduce a semaphore in between the server and these threads. And I'll do the same type of diagram that I did before with the mutex, where I show each step. So this semaphore of length of 2. So basically, I'm going to continue to draw this diagram. I'm going to do it similar to the way we had it before, because I just don't have space. Let me just delete these. I'll copy them again. Okay. So before, the rule is that you have to acquire the semaphore before you can talk to the server. That's going to protect the server. So thread A, let's say thread A come here. All right. So it's going to do an acquire, and we'll say 1. And then concurrently with that, we'll say C does its acquire. And then thread A and thread C will be allowed to do their requests. But thread B and thread C, they can't acquire. These acquires are not going to work. They're going to block. And that's going to block their request to this slow server. So let me remove these numbers because we haven't assigned a number yet. So right now, only thread A and thread C are allowed to make their requests. So we do acquire, acquire, post, post. Now, once thread A and thread C are done, in any order, it doesn't matter, they will release. So we'll add another error here. And let me see if I can move this text. Yeah, I think I can move it up that way, yeah. So we'll say this is step 5. Will be a release. And then over here, you'll have thread A do its release, which will be step 6. And these can happen in any order between thread A and thread C. You know, thread A could do its release, thread C can do its release second. That doesn't matter. What matters is, regardless of the interleaving of events that happen here, we have a system that's constrained in how those interleavings can progress the system entirely. And in this situation, the semaphore is limiting the progression of 2 or anything but 2 of the threads. Only 2 of the threads are allowed to make progress. In this case is A and C, but in any other interleaving of events, it could have been B and C or B and D. So it doesn't matter that it's thread A and thread C, and it doesn't matter that thread C released first and thread A released second. Like, these are all different. There's all these different permutations of events and interleavings of events that can happen in any order. But what we want is a system that no matter what happens, you know, we are guaranteed to have the correct result come out. So in this situation, thread C released first, thread A released second. And as soon as thread C released, that allowed thread B to then do its acquire. So we're going to say 7 here. It does its acquire. And then thread D will actually, we'll just say thread D, actually it already has an acquire. We're going to say that waits. So thread B now has its acquire, and then it's going to be able to do its post. So we can say 8 up here. And then let's say like 9, it does its acquire down here. And then it's able to do a 10 post up here. And then finally, thread B, since it's done with its post, it's going to do a release, which will be 11. Release. And then finally, thread D is going to do its release. So these are like, you know, the basic primitives of concurrent software. Yeah. Sorry, I got backed up on the chat here. So mutex is always only one at a time rather than semaphore depends upon server concurrency. Exactly. That's a good way of framing it. With the mutex, the way I would say is the mutex, only one thread is allowed to make progress on the work that needs to be done, whereas a semaphore allows potentially more than one. And in the book, they talk about this this binary semaphore, implementing a binary semaphore protocol. That's basically a mutual exclusion lock that they're describing here. So they have the reserve semaphore. Well, that's a lock. That's locking a mutual exclusion lock. And then they have a release, and they even called it a release because it's obviously a release. So it's a bit of a different terminology and a bit of a different implementation. But ultimately, that's the way I view things, is that semaphores are like a general concept, and a special case of a semaphore is a mutual exclusion lock. Like several times in the book, he describes a semaphore as being implemented as an integer, and there's many different ways that you can implement semaphores. Like I mentioned before, Go has a semaphore that's implemented as a channel. So it doesn't have to be an integer. A semaphore as an abstract data type. Abstract data type. They don't, I'm sure they have it here. The other thing is that semaphores were originally conceived by Dijkstra. I learned that from the reading today. So some of the notation is like kind of Dutch, because I think he was Dutch. Yeah. I want the abstract data type. But yeah, you can just Google for it. Let's see. So mutex is a mutex is a mutual exclusion lock. So there's an article on locks. Yeah, if you search for mutex, I mean, it's pretty much a mutex is a lock. Another term that you'll see is like critical sections. So a mutex can guard resources, but the way that they do that is you define what are critical sections of your code, which is the code that's actually accessing those resources, and you lock and unlock around it. So in this case, the critical section of this code would be the increment of the balance, and then down here would be the decrement of the balance. This would be a really good article if you're unfamiliar with mutexes, because this Java code here is very straightforward. In fact, I can do a Go program if you want to see something like real life here. So we'll just do main.go, package main, and we'll say main func. It's been a while since I've written any Go, so so in here, this is noisy. We're gonna say var balance. So to use their example with like an account balance is equal to 0. So say I have no money, and we'll make this a int 64. And then in the main, we're gonna have one Go routine, which is kind of like a thread. You can think of it as a thread. And it's gonna basically count to 100, or we'll say count to 1,000, or let's do 1,000,000. So for actually, I don't need the parentheses. For I is equal to 0, then I is less than 1,000,000. And then we do I plus plus, and then in here we say balance plus equals 1. And then we have 2 of these Go routines here. We're just gonna have the main thread do the other access here. And then once, actually no, let's do 2 Go routines, and then we'll do a wait group. Var wait group sync.wait group, wg.add 2 defer wg dot was this done? Yeah. wg done, and then down here we'll wait. wg dot wait, and then we'll just say println out balance. We'll do a printf, fump.printf. Balance is %d here. We'll give it a new line and give it balance. So what this is describing is having two concurrent threads, incrementing my balance to 2 million effectively, because you have this first go routine will increment the balance to 1 million. And then this second go routine will also increment the balance by 1 million. I should say by 1 million. So at the end, what do we expect? Well, we expect that after both of those go routines are done, so we wait for them to be done, then both we expect the balance to be 2 million, because there's two go routines incrementing it by 1 million. So if we run this program, the balance was not 2 million. We're about 500,000 off. And it's different each time. Every time I run this program, it's basically like the value will be based on all these different variables of like the Linux kernel scheduler, the Go runtime scheduler, cosmic rays coming through the atmosphere and hitting my computer. Like there's so many different things that like can interfere with the timing and the interleaving of different events to make it to where this isn't the correct value. So to fix this, you would add a mutual exclusion lock. So let's go ahead and do that. So above here, you just say mu sync.mutex. So this protects, this mutex now is going to protect the balance. So now I have to use it. So whenever I increment, so in our example over here, you see how he's taking out the lock around the increment. So around our increment here, we want to just say mu.lock. And then we need to release the lock once we're done. So then we say unlock. So we do the same thing down here. If we don't do it in both places, then we'll still have issues. So both of these threads, both of these Go routines are now collaborating on incrementing this value, and only one is doing the increment at a time. So it's limiting the parallelism because you can only have one of these Go routines running in these critical sections at any given time. So it's limiting our parallelism, but it's giving us a correct result. So when we run this again, we get 2 million. And we get 2 million every single time. Because it doesn't matter how these things interleave and how the kernel and the Go runtime schedule these threads and Go routines. None of that matters. The only thing that matters is that does the Go routine have access, mutual exclusive access to that memory? And it does when it needs it. So I basically, this main here is basically like the Go version. Let me just give you a better view here. So this Go program, is basically very similar to what they did here. And it's a very typical example, to be honest. I've like written this like a dozen times. Yeah. Cool. Let's continue on with the reading. So let's see, we're at what page here? Yeah, 997. And it is 427. 427. Okay. All right. What we got going here? Clear. All right. Kill this. I'll come back to this later. All right. System V shared memory. So they're going to be using a semaphore here to protect the shared memory. I already know that they're doing that. There's some really interesting diagrams in here, like this one down here, this one here, which I've seen previously, absent the shared memory stuff, but it basically it'll show you how like memory is laid out and virtual memory is laid out for the process, which is like it's a very important model to like keep in mind when you're thinking about memory. It's like I'm sitting in class. Yeah. All right, so let's dive into this. This chapter describes System V shared memory. Shared memory allows two or more processes, or threads, or go-routines, or whatever, to share the same region. Usually, I guess in this case, it would be processes only. Usually referred to as segment. A physical memory. Since a shared memory segment becomes part of a process's user space memory, no kernel intervention is required for IPC, so that reduces syscall overhead. All that is required is that one process copies data into shared memory. That data is immediately available to all other processes sharing the same segment. This process provides fast IPC by comparison with techniques such as pipes, message queues, etc., where the sending process copies data from a buffer in user space into kernel memory and then receiving process copies in the reverse direction. Each process also incurs the overhead of system calls to perform the copy. So basically, like all the IPC stuff that we've done so far has incurred multiple copies in and out of user space and kernel memory, along with all the context switching involved with making a syscall, which is very heavy-handed and limits performance. Shared memory is like way more faster than anything else. In fact, I would default to using shared memory for almost everything. But some people disagree. And those people don't care about performance. On the other hand, the fact that IPC using shared memory is not mediated by the kernel means that typically some method of synchronization is required so that the processes don't simultaneously access the shared memory. So that's when we're getting into the semaphores and mutexes. Two processes performing simultaneous updates, or one process fetching data from the shared memory while another process is in the middle of updating it. System V semaphores are a natural method for such synchronization. Other methods such as POSIX semaphores and file locks are also possible. You could also just use a regular mutex because it's shared memory, right? I'm pretty sure you could just use a mutex that's allocated in the shared memory. Like Go has a mutex. Yeah. I'm curious about because the problem with using these freaking semaphores that even the POSIX ones, but the System V ones as well, is that you have to do syscalls. And there's this thing called the futex in Linux. So this is like fast user space locking. So I would probably use this thing instead of POSIX semaphores or System V semaphores. I would rather use this thing. There is a syscall for it. Let's do a man on futex. It uses macros, but it does say that it's in user space. Let's just ask AI real quick. In Linux, is futex fully in user space, or does it require syscalls? It might just be one syscall to set it up. most user space, but absolutely does require syscalls in the contended cases. Okay, so it fails over to syscalls when it's contended. Uncontended fast path stays entirely in user space, and the kernel only gets involved when threads actually need to sleep or wake. That makes sense because you're doing a sleep or wake. You're already talking to the kernel. That makes sense. I would use this. I think this would have like much better performance than using a semaphore. Few texts can handle conditions. When you say handle conditions, do you mean like condition variables, or you mean something else? So what really is shared memory? Doesn't memory is shared among the processes? So each process in the operating system has its own virtual address space, and it does not share memory by default. So process A and process B will not share memory. So what systemv shared memory is doing is it's allowing us to mark pages of memory, or I guess they call them segments, as shared between multiple processes, so that you break down the boundary. And the idea being that while the memory, the physical memory that backs these segments is the same between the different processes, the virtual addresses of those memory segments are not the same, or are likely not the same, I should say. They could coincidentally be the same. So you're still having separate virtual address spaces. You just happen to be mapping in the same physical pages for the same physical memory. And like that gets into like operating system virtual memory stuff, which is like a whole discussion in of itself. But yeah, let's continue on here. Systemv semaphores, yeah, you're talking about, yeah, okay. In mmap terminology, a memory region is mmapped at an address, while in systemv terminology, shared memory segment is attached at an address. These terms are equivalent. The terminology differences are a consequence of separate origins of these two APIs. Mmap is the API that I'm most familiar with. I'm not familiar with systemv shared memory at all because it's like kind of like legacy at this point. Let's see. Is there any lock which can be conditioned? So what really the difference between mapped and attached? There is no difference. It's just terminology. Sometimes like the author will call these things out in these little small paragraphs, just kind of like details about like terminology and stuff. It's not really important. It's good to know if you want to be able to read what people write about this stuff. Overview. In order to use shared memory segment, we typically perform the following steps. So we call shared memory get to create a new shared memory segment or obtain the identifier of an existing segment. This call returns a shared memory identifier for use in later calls. Use shared memory at or attach the shared memory segment, that is, make the segment part of the virtual memory of the calling process. At this point, the shared memory segment can be treated just like any other memory available to the program. In order to refer to the shared memory, the program uses the adder value returned by shared memory call, which is a pointer to the start of the shared memory segment in the process's virtual address space. And then we call shared memory DT, which detaches, so to detach the memory segment. After this call, the process can no longer refer to the shared memory. This step is optional and happens automatically on process termination. And then we call shared memory CTL to delete the shared memory segment. The segment will only be destroyed only after all currently attached processes have detached it. Hold on. The segment will be destroyed only after all currently attached processes have detached it. Only one process needs to perform this step. So not only do you have to have everyone detach, but you also have to explicitly delete it. That's like horrible. All right, creating or opening a shared memory segment. The concern I have with this is that um, most APIs in Linux that are file descriptor based, if you terminate the process, the file descriptor counter will decrement, and once there's no, file descriptors that are still available in the system, it'll automatically garbage collect. Basically, file descriptors are reference counted, and none of the system v IPC stuff is reference counted. So you have to do all these like explicit calls. And the concern I have is like, what if I like map in a bunch of memory, I do some operations like several gigabytes, and then I never delete it, even though all the processes that had references to that memory have gone away, like it'll still be in the kernel somewhere, and you'll have to manually delete it with IPCs. So IPCs is the command that lists out the shared memory segments here. You can see I don't have any here. So that could be like a memory leak for the kernel. Creating or opening a shared memory segment. The shared memory get system call creates a new shared memory segment or obtains the identifier of an existing segment. The contents of a newly created shared memory segment are initialized to 0. Oh, cool. That's cool. I didn't know that. So you just give it size and some flags. The key, we've seen before how we generate the key. The key argument is generated using one of the methods described in section 45.2, or you can just say IPC private. When we use shared memory get to create a new shared memory segment, size specifies the positive integer that indicates the desired size. Let's go ahead and do a C program here. So I'm going to make dir on, what is this, chapter 48. And I'm going to move my main.go into there just because I don't want to lose it. And then let's move into chapter 48. And then actually I need to find a make file. And I'm going to copy my chapter 44 make file into chapter 48. Oops. Along with, I think I want the .get ignore as well. Oh, I don't have it, get ignore there? That's not good. Chapter 44, make get status. Get status dot. Yeah, we need a get ignore there. So I'm also gonna do a find, but this time for dot get ignore. Copy chapter 43 into chapter 44, and also, oops, dot get ignore, and then also into chapter 48. Just want to make sure I don't commit any of that stuff. Okay. All right. So in here, I'm just gonna vim up a memory get. I'm just gonna call it memory get. Shared memory get.c. And we'll have a main in here. I don't want any arguments. Keep it super simple. I'll include a standard lib.h for these symbols, and then we're gonna call, so we need some more stuff here. We need sys types. Oops. And we need sys shm.h. So in here, we're gonna call shm get the key. We can just say is IPC private, and the size will be like, we'll say 1K. That's a megabyte right there. We'll do a megabyte. The flags I'll leave as 0, and then we'll say this will be the ID, and we'll say int ID, and then we'll printf out the ID is %d, and we'll give it a new line, and we'll say ID here. We'll need standard IO for printf. Okay. So in here, I can do make now, and I can run. If I do IDS, if I do IPCs, I don't have any shared memory segments, but if I do build and run my shared memory get a couple of times, so now I should have 3. Yep, I have 3. Futex weight bit set. So with Futex, we can prioritize any specific order which can't be done in semaphore. I'm actually not super familiar with Futex API, so you might actually be ahead of me on reading about that. Let's see, weight bit set. Okay, so this selective Futex waiting and waking. Except it's used to provide 32-bit max to the kernel. This bit max in which Yeah, to be honest, I'm not super familiar with this API. But it looks like selective waiting and waking. So it's like a wait, except that the value is used to provide a bit mask to the kernel. This bit mask, in which at least one bit must be set, is stored in the kernel internal state of the waiter. See the description of Futex wait bit set. Okay. Oh. Let's try to find that. This bit mask, in which at least one, yeah, okay, is used to select which waiters should be woken up. Okay. So basically, when you're waiting or waking, you can have this bit mask provided, and when you release the lock, the kernel will wake up the people waiting, the concurrent threads waiting that match the bit mask. So that can give like and wait. All of the waiters for which the result of the AND is non-zero are woken up. The remaining waiters are left sleeping. So just because they're woken up doesn't mean that they will acquire the mutex. It's kind of like a mechanism for waking up more than one thing that's waiting on the lock. Mutex can only entertain single thread. Semaphore can do multiple, but the order can't be conditioned with Futex. We can condition the priority. Searching if you can apply condition to any certain lock. I don't know if I'm right or wrong. So mutex just means that when the mutex is acquired, there's only one thread of execution in that critical section. But you can have any number of threads contending for the mutex, trying to acquire it. The semaphore is indeed multiple threads, yeah. Yeah, and the futexes, like I know of them. I've used them through libraries that use them, but I don't have much experience with the API directly. But what's good is later in the book here, there is a section on Futex that I am I thought there was. Maybe it's not in the, let's go here. Wow, there's a lot of stuff. Okay, we're close enough here. Futex weight constant. It's a 1090. Futex. I thought it was in the index. Futex. I guess it's not a topic in and of itself. It's just referenced a lot of time in the book. There is a reference here, Drepper, from Red Hat. Futexes are tricky. That's a bummer. I thought they would have an explicit section on it. Fuss, Futex, and Furewalks, fast user level locking in Linux. So that's from kernel.org. So that's a white paper about fast user space locking. Okay. Yeah, I guess there's no explicit section of the book on it. That's a bummer. Okay, where did I leave off here? Oh, we wrote this program that created these shared memory segments, and then might as well do one that deletes them, right? CP shared memory get to shared memory. We'll say RM. Okay. And then in shared memory RM, we're going to go in here, and the call that he mentioned was shmctl. And if we pull up the man page for that, man shmctl, it is going to be IPC RMID. The ID I'll have to provide though, and then this is going to be IPC RMID. And if we go back up here, we don't care about that. That can be null. But we'll need to parse out the we'll take what is it? I need to take an argv here now. So this will be integer arg c and a char star argv array. And then here we're going to say parse, or say a to I of arg v sub 1. And that'll give us back our ID. Oops. And then we can pass in the ID here. Okay. Let's go ahead and make that. And then if I do IPCs, I can then run build shared memory RM, and I can give it 1. And that deleted 1, or I could give it 3 here, and that deleted 3. So it's a pretty straightforward API. I mean, all these APIs are super straightforward. Okay, let's continue reading. I mean, all this is the same as like the last chapter. This is different. We'll say the above flags are described in more detail, blah, blah, blah. In addition, Linux permits the following non-standard flags: shared memory huge table, a privileged cap IPC lock process can use this flag to create a shared memory segment that uses huge pages. Huge pages are a feature provided by many modern hardware architectures to manage memory using very large page sizes. For example, x86-32 allows 4 megabyte pages as an alternative to 4 kilobyte pages. On systems that have large amounts of memory and where applications require large blocks of memory, using huge pages reduces the number of entries required in the hardware memory management unit's translation and look-aside buffer. This is beneficial because entries in the TLB are usually a scarce resource. See kernel source so-and-so for more information. And then there's shared memory no reserve. This flag serves the same purpose as shared memory get as the map no reserve flag. On success, shared memory get returns the identifier for the new or existing shared memory segment. Using shared memory. The shared memory system call attaches the shared memory segment identified by shared memory ID to the calling process virtual address space. So this is attaching it. So I'm going to copy my shared memory RM to shared memory attach.c. And then in here, can I just, no. Let's grab that. Here, I'm going to do the same parsing of the ID. And then this is going to be shmat. I'm going to give it the ID and then the address that I want to point it to. So originally the size of this was this big. So I guess I don't really care where in memory it is. Like it already knows what size it is. Why would I want to? Yeah, I'm just gonna give it null for the address. Null. And then flags, I'm gonna give null as well. I'll give 0 for flags. Think about a pointer to integer conversion, which, oh, because I said result was integer and it gives you back a pointer. Yeah, so this result will be a void star. And I'm going to say P here. We'll say pointer. And first byte. We'll say first byte is going to be that 0. But this needs to be cast to a, I'm going to say a char star. And this needs to be a typecast to a char star. And then this needs to be a D. Yeah, that'll work. IPC stands for inter-process communication. It's just a way to have multiple processes communicating with each other. So network would be a form of IPC. All the capabilities of System V, IPC. POSIX has its own IPC. Memory mapping, file-based, what do they call it? Memory mapped file IO would be a version of IPC. The file system, I guess you consider that a version of IPC. I mean, typically that's not something that is considered IPC, but it is a way of allowing processes to communicate with each other. So in a general sense, that's what IPC is. Methods of allowing processes to communicate with one another. So this program just attaches the shared memory to a place in my virtual memory address space, prints out the pointer that it attached to, and then prints out the first byte, which should be a 0. So let's make that up. And then I'm also going to just write the program to set it to. So CP shared memory attach. I'm going to say shared memory write .c, and this thing is going to have two arguments now. It's going to be value. And we'll make it a number as well. That's fine. That's good. Value needs to be declared, obviously. Value. And then we have our pointer. And then we're going to do our write, which would be result 0 is equal to value. And I'm going to delete this. Printf. All right, let's go ahead and make all this up. Make. And then if I do IPCs here, there's nothing running. So I'm going to run build shared memory get. So I have ID 4 now. So I'm going to say shared memory attach. And that's going to be 4. It's a pointer to a segmentation fault because it's an error. That's -1 in 2's complement. Okay, so something went wrong there. And let's get out of here. Come on. Shared memory attach. So it gives back a void star. I convert it into a char star. ID, adder null, flag 0. All right, well, let's learn more about attachment because I'm getting a little bit over my skis here. So the SHMAT system call attaches the shared memory segment identified by SHMID to the calling process virtual address space. The SHM adder argument is the setting of the SHM rand bit in the SHM flag bit mask argument. Sorry, the SHM adder argument and the setting of the rand bit in the flag bit mask argument control how the segment is attached. So if SHM adder is null, then the segment is attached to a suitable address selected by the kernel. I'm happy about that. This is a preferred method of attaching the segment. If it's not null and random is not set, then the segment is attached at the specified address, which must be a multiple of system page size. If it's not null and random is set, then the segment is mapped at the address provided by, rounded down to the nearest, oh, it's a rounding thing, that was random. Rounded down to the nearest multiple of the constant, SHM LBA, low bound address. This constant is equal to some multiple of the system page size. So I need to check for -1. So here we say if result is less than 0, then we're going to p error out from SHMAT, and we're just going to exit. And actually, we can just return exit failure. Okay, so let's go ahead and make that, and then we'll run it again. Why didn't it literally segmentation? Okay, so it's all ones. So I guess it's interpreting that as not -1, which it is, because let's just get like a void star out here. Void star result. And we'll call this adder. And then down here we can say adder is equal to the char star of result. Yeah. And this will be adder. And this will be adder. Still freaking out. Okay. It didn't error out, but it gave me all ones for my pointer. Maybe if I say here integer of result cast to a smaller integer type int from void star. That's a warning. Let's see if they have an example in the book here of how to do this. So obviously I'm not doing it right. Okay, so we have to cast the constant to -1. Okay. And we have to do an equality. Yeah, we have to do an equality comparison. Okay, so this will be result is equal to a void star of -1. Okay, now that'll error out and give us a P error. Permission denied. Okay, that work? No. First byte is 0. Okay. Okay, so I guess you have to have special privileges. It's probably because I messed up when yeah. Let's do a IPCs again and do build shared memory RM4. If I could delete it, I think it's because I didn't set permissions on it. That's why. So I don't want to use sudo for that. So I'm going to say shared memory get. We'll need to have the flags of, there has to be an example here because I don't know them off the top of my head. Okay, so I'm going to say IPC create, obviously. I don't even think I need to specify that. And then the object permissions, which are set in a header somewhere. Yeah. So I'm just going to say 0600. And I don't think I even need this IPC create. I think I can just say, hey, just set those permissions. Okay. So IPCs list nothing. If I remake my stuff, build shared memory get, IPCs now has 5 and has its permissions set now. So now I can say attach to 5 and that happens. It's fine. Oops. It just reads the byte 0. And then if I say, hey, I also want you to write to 5 the number 12. And then I do my attach. I now have 12 written in there. Pretty cool. All right, let's go back here. Where did I leave off? Left off around here. Explain in easy words for a minute, please. So the easy words here is that there's a command called IPCs. And when you run that, it lists out all of the different IPC objects you have in the kernel. And these things live inside of the kernel. They're not part of the file system. They live inside the kernel. And so you can see I have this shared memory segment with the ID of 5. And I wrote these programs just now to experiment. So I have one called shared memory get, which will create a new shared memory of a million bytes. So if I do that again, you can see now I have one called ID6. So IPCs now has a 6, and it has 1,000,000 bytes. So the other one that I wrote was shared memory attach, and you give it the ID. So in this case, I can do 6, and all it does is gives you the pointer in the virtual address space of where it was attached to. And then it also reads the first byte of the memory. So there's 1,000,000 bytes, but I only care about the first byte. And the reason why I printed out the pointer is that I wanted to illustrate that every time you run this program, it'll have a different address here. You see how these addresses are different? So the kernel is just putting it wherever it wants in your virtual address space. But as long as we know where it is, the kernel tells us where it put it. Like we're okay. And then the other program that I wrote was a write program. So this allows me to actually write to the memory. So I can say write to 6 the value 37. And now when I do my attach and read, the first byte says 37 instead of 0. And if I do IPCs here, you can see I still have 5 and 6. So now I can read from 5, and it says 12. And I read from 6, it gives me 37. And all this memory, it's not stored in a file system. It's not stored, it's not persistent anywhere. It's just resident inside the kernel. So each time the kernel swaps the address as it seems fit, yeah, it just puts it wherever it wants. It would never be the same address. I mean, it could be just coincidentally, but it's almost likely not going to be the same address. And that's controlled by some parameters here. Like you can tell it, map it to this specific address if you really want to, but I'd rather have the kernel just decide that. So it's not the same case for the process, or it's with them too. What do you mean by that? And then I also wrote this program, build shared memory RM, so I could just delete these things when I'm done with them. I mean, I didn't need to write these programs. I just did it to get a feel for the API. I mean, everything executing by CPU always has different addresses. So there's the physical addresses of the memory, and then there's the virtual addresses that your program uses. And so everything that we're dealing with is like the virtual addresses, and those can be the same. They don't have to be different. You can have, 3 different programs all reading and writing to the same memory address, and those actually map to different places in memory on the computer. Because a memory address in a program is a virtual memory address. It's not an actual real memory address, if that makes sense. It's all part of like Linux's, if you Google like Linux virtual memory, yeah, this would be a good diagram here. So virtual memory per process maps onto physical memory. And some of these address spaces in your virtual memory can actually map to disks. That's the memory mapped IO. Yeah, this is a good example. This is on Wikipedia. If you search for virtual memory, it's like the first thing that comes up here. It's important to understand. I've never read this Wikipedia article because it's a pretty straightforward concept, but you could get a good feel for it by reading this. And like every computer has this thing called a memory management unit. So that mapping between virtual address and physical address is actually handled by hardware on the computer instead of in software by the kernel. The kernel sets up the memory management unit when it initializes the computer, but all the mapping is being performed by the memory management unit. Otherwise, it would be horribly slow. Cool. Let's continue on with using shared memory. Yeah, I think we got past that. We were down here. So when you assign the virtual RAM to a disk, it's just assigning a virtual address to that disk. Yeah, exactly. Specifying a non-null value for the adder, either the second or third option listed above, is not recommended for the following reasons. It reduces portability of the application. An address valid on one Unix implementation may be invalid on another. An attempt to attach a shared memory segment at a particular address will fail if that address is already in use. This can happen if, for example, an application perhaps inside the library function had already attached another segment or created a memory mapping at that address. As its function result, shmat returns the address at which the shared memory segment is attached. The value can be treated like a normal C pointer. The segment looks just like any other part of the process's virtual memory. Typically, we assign the return value from shmat to a pointer to some programmer-defined structure in order to impose that structure on the segment. To attach a shared memory segment for read-only access, we specify the flag SHM read-only in the SHM flag. That's cool. We can use that. So we do shared memory attach. This one we could say here SHM read-only, and that'll make it read-only. And when we run our IPCs, we don't have one, so we have to run build shared memory get, and then we'll run attach now on 7. And because I want to do another write, I'll write 1337. Oops, sorry, 71337. And we'll then do a read attach 7. Bam. Why did 1337 not come through? Is that too big? Yeah, it's too big for a single byte. So 255 would be the max value. And that's interpreted as a -1 because we're in 2's complement. So we can actually just go to 127 as the max value. Because I think 128 would be negative. Yeah. So we go 127. Boop. Cool. All right. So that's read-only. To attach shared memory segment, process requires read and write permissions unless read-only is specified, in which case the read permission is required. It's possible to attach the same shared memory segment multiple times within a process, and even make one attach read-only while the other is read-write. The contents of the memory at each attachment point are the same. Since the different entries of the process, virtual memory page tables are referring to the same physical pages of memory. One final value that may be specified in shared memory flags is shared memory remap. In this case, adder must be non-null. This flag requests that shared memory at call replace any existing shared memory attachment or memory mapping in the range starting at the adder and continuing for the length of the shared memory segment. Normally, if we try to attach a shared memory segment at an address range that is already in use, the error invalid results. Remap is a non-standard Linux extension. I don't quite understand that. Table 48.1 summarizes the constants that can be ordered in the flag argument of attach. When a process no longer needs to access a shared memory segment, it can call DT to detach the segment from its virtual address space. The adder argument identifies the segment to be detached. It should be a value returned by a previous call to attach. Okay. Oops. Let's see. Detaching a shared memory segment is not the same as deleting it. Deletion is performed using the control RMID operation as described in section 48.7. Child created by fork inherits its parents' attached shared. Did I fix the chair? Yeah. Yeah, I fixed the chair. Sorry, I was like distracted because there's some like police or something running their sirens outside. Yeah, the chair, I tightened it up, fixed it this morning. And I don't know if you noticed, but the Discord is set up. So if you want to join the Discord, I created that this morning. Yeah. Let's see. If you go to twitch.tv cypher, if I can spell right, twitch.tv cypher 0 dev. So I have my links down here now. So you can click on Discord. And you can accept an invite if you haven't already. I think you probably have because it says 2 members now. Yeah, I don't have a bot set up yet for anything. I do not have any pets. I do take care of people's animals though, for long periods of time sometimes. Create a book channel. Let's just start off with one channel because I don't think we're gonna have like a lot of people in there yet. But yeah, I don't know. I'm not really huge into Discord, so maybe I need to spend some time building it up. But yeah, let's book channel and also a lesson. Let's do transferring data via shared memory. Example. So this is a good example. We now look at example application that uses sysv shared memory. How much more? I think we got about 20 pages left. So we are shared memory, which will be 16. So we got 15 pages left. I think actually what I'm going to do is I'm going to take a break here for dinner. Because I'm freaking starving. And I'll get back on after dinner to finish up this chapter, which is about 15 pages, which I can read if I just read. I can read 15 pages in an hour easy. So we'll finish up this chapter. I'll probably get back on 6:30, and then we'll finish up by 8 at the latest. So we are at page 1001. We have crossed 1,000 pages in this book. That is an accomplishment right there. I'm proud of myself. Before I log off, though, I'm gonna just like do some cleanup here. So I'm just gonna full screen, get status. So I got 43, 44, 46, 48. I'm gonna RM chapter 48 dot. I don't need that. And then progress. So I got 44, 43. Those are just okay. And then LSHLA chapter 46. Yeah, just a design doc. And then LSHLA chapter 48. Okay. And then if I do get LGA 1, I think 46. Yeah, 45, 46. So I'll clean that up when I get back on. Cool. I'm gonna eat some chicken breast because I need my protein and some sides. I haven't decided on the sides yet, but I'm gonna go do that now because I'm starving, and I'll be back on probably in about an hour. So about 6:30ish, I would say. All right. Cool.